Newton's laws of motion, just some intro. It is formulated by English physicist and mathematician Sir Isaac Newton. I'm sure almost all, not all of you, would have heard of this guy. So this guy, legend has it that he sat under the apple tree and then the apple fell on his head. Right? So he discovered gravity. So it's this guy. His laws of motion, there are in total 3 laws. We'll go through them one by later, and then we'll see what they are. So this describes the relations between forces acting on the body and the motion of the body. So the motion, remember, the motion we are talking about kinematics. Now we are moving into this part, okay, the forces that's causing the motion. And Newton's laws of motion is the foundation of classical mechanics, which is what mechanical engineers will be doing most of the time. Okay, classical mechanics. So for classical mechanics, and for this module, we only deal with objects that are very large compared with atomic dimensions. And you know, atomic dimensions and the quantum realm, all that. If you all go watch Ant-Man, right? So those deal with the dimensions which are very, very small. So if you get to that very small dimensions, right, forces will behave differently. Okay? And also, if you get to the very large side, for example, if you all watch space movies about black holes, all those stuff, right? Those forces will also behave a bit different. Okay, and then also whatever we are going to learn, right? It is for speeds. V is velocity, right? That is much smaller than speed of light. C is speed of light. We won't talk about speed of light in this module, okay? But for us to apply Newton's laws, we need to know that it's only for things that are much slower than speed of light, which is almost everything that we can see with our eyes, right? Okay, before the 3 laws, we need to first understand the concept of force. So what is force? Force represents the interaction of an object with its environment. And these are some characteristics. When an object is at rest or uniform velocity, at rest means not moving. Uniform velocity means it can be moving, but then the speed doesn't change. Okay, so uniform. So when it is in those states, right, we say that it is in equilibrium. Not, a net non-zero force on an object causes it to accelerate. Okay, this means that if you have a force, okay, if you apply a force, it will cause the object to start to move. Okay, if you apply a force, it will cause the object to start to move. There are in general two kinds of forces. One is the contact force, which represents the result of physical contact between two objects. Okay, literally it came from that meaning, right? That's why we have the name here, contact forces. For this kind of forces, right, it is only present during the contact. So when it's touching each other, right, then there is this contact force. Okay, let's say my right hand touching my left hand, I touch each other, then there's a contact force. And this force does not remain in the body when the contact is over. So when I release my hand, right, or when I stop holding my water bottle, when I put down my pen, right, the contact is over and there will not be this kind of contact force anymore. Okay, so that's one kind of force. The other kind, right, of forces is the field forces. They do not involve physical contact between two objects, but act through empty space. So examples of this kind of field forces, right, they are electrical, gravitational, magnetic is also one of them. So it's just in this space, right, you put a magnet, for example, a magnetic field, right, you put a magnet, it will just get attracted. Okay? Same for electrical field. So these are field forces, happens within a field. For our course, right, we will focus a lot on contact forces, not on field forces. Okay, some examples of forces. Forces when kicking a ball, when you want to kick a ball, when you want the ball to move, right, you have to kick it. When you kick it, you apply a force. Okay, then when you, for example, you are dragging up a box along a slope, you want to drag it up, right, you have to apply a force, okay, to let it move in the direction that you want it to. And then springs, also spring, there is a force associated with it. If you have to press it in, right, to compress the spring. So you apply force to press it in. And then when you apply force to press it in, right, the spring will somehow apply a force outward also. So these are all forces that's happening. So force is a vector. When we say vector, right, means it has magnitude and direction. Okay, direction is very important. We need to know where we are applying the force. We push to the front, push to the right, push to the left, right? They are all different, okay? Can be the same magnitude, but the outcome will be very different, as we would expect. Resultant of forces acting on object. So for example, right, because it's a vector, let's say if we have this box, and if you apply a force to the right, you pull at this tip, you pull to the right, and then you also go and pull at the same tip, you go and pull to this direction, F2. Okay, it's more to the top, but a bit to the right. Okay, so these two forces, right, they all act on the same point. Because forces are vectors, right, we can sum them up. So in the end, right, when you apply F1 and F2 in this manner, it's the same as applying this resultant force. Okay, so resultant equals to F1 plus F2. This is vector addition. Okay, so remember how to do vector addition? We have gone through in the previous lesson. So there's two forces, right? But in general, for more than two forces acting, you will just sum them up. Okay, F1, F2 plus F3 plus F4 and so on. You will just sum them all up like they are vectors. So you will be doing vector addition. And also because they are vectors, you can resolve into perpendicular components. For example, now we have a box here. You apply a force here. Let's say you tie a string and then you try to pull it. That means you apply a force here. Okay, so this force, right, is one force that you're applying, but you can resolve this into two perpendicular components. And usually we do it in the right direction, correct? So one can go to the right and one can go upwards. In other words, this force that you apply can be equivalent to you pulling upwards with Fy and also you pulling to the right with Fx. So let's say the box, right? Let's say if the box got filling, let's say if you're on the box, you will not be able to tell whether the person pull like this or there's two hands pulling up and right. Okay, you will not be able to tell because it's exactly the same force. Any questions so far? Should be okay lah, huh? Just intro to forces. So now we come to Newton's first law. Textbook definition. It states that if a body is at rest or moving at constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon by a force. So, okay, when I say textbook definition, I means this is a long definition that is trying to describe first law, but there is no need to memorize this kind of statement. If you all had taken Cambridge O levels, A levels, that kind of thing, right? They would want you all to memorize. Okay, but then now we are at the uni level, and then to make things work, right? Memorizing this kind of statements, it doesn't help at all, right? You go out work, let's say you go outside and work, you also don't need to memorize this kind of thing, right? So we will just learn how to apply. We don't need to memorize this kind of statement. Okay, but I will usually put the actual definition here so that we know the actual definition. Okay, so what this first law is talking about, right, is trying to say an object when it's at rest or moving at constant speed, that means speed don't change, it will continue its motion or it will not move unless you go and apply a force to it. It's a bit common sense, but this is Newton's first law. If you don't do anything to the object will remain its motion or remain at rest. If you want the object to change its motion, right, you have to apply a force. Okay, so this is what first law is talking about. And also it's from this first law, that we have the concept of inertia, which is the tendency of an object to resist any attempt to change its velocity. For example, a bowling ball is more resistant to changes in its velocity than a basketball. We say that it has greater inertia. You all got throw bowling ball before, right? Much heavier than a basketball. So we will feel that it's so much more difficult to throw a bowling ball. So in that sense, right, bowling ball has greater inertia. Also, English, right? Colloquially, sometimes we say, wow, very high inertia to get work started, very high inertia for me to wake up. Okay, so that inertia, right, when we refer to it, actually it stems from physics. Okay, this is the actual definition. Some examples of Newton's first law. Golf ball starts moving. So a golf ball initially at rest, you must go and apply a force, then the golf ball will start to move. If not, it will remain at rest. Cyclist continues in motion. So imagine this cyclist is cycling to the left, correct? Then it hits a stumble on a block here. Because the block stops the bicycle stops. But the guy, the man, right, nothing is trying to stop him from moving forward. Okay, so he would tend to want to move forward. That's why you, if your bicycle gets stopped by something, right, you will want to fly forward. Okay, it's the concept of inertia because no force is trying to pull you back. Astronaut continues in motion. In space, right, there is almost no force acting on you. Okay, imagine there's no force. So zero force. If you are floating away from Earth, you will continue to float away. Okay, unless you apply a force to counteract that. That's why they carry some jetpack at the back, okay, to shoot gas in the opposite direction so that they can move wherever they want. If you watch sci-fi shows, right, actually they will always portray this kind of event as very dangerous. If they run out of fuel, they can never come back to Earth or their spaceship. Okay, another illustration to explain first law. The first one on the left here, okay, it shows a girl on roller skates inside something that looks like a train, right? So she's here, everything is at rest, t equals to 0. After a while, the train accelerates. As acceleration going to the right, so the train will start to move to the right. But you see the position of the girl, right? Let's say if there's no friction, very slippery, right? She would want to stay put. Okay, she will want to stay put. She will not want to move. That's why when you stand on the train start to move forward, right? You will feel that you want to move backwards. Actually, you never fall backwards. Lah. You are trying to stay on the spot, but because the train move forward, you feel like you are falling backwards. Okay, that's Newton's first law. And also sort of explain inertia as well. Okay, on the right is actually later, right, when the train and the girl they are moving forward already. Then now the train want to come to a stop. Okay, now the train want to come to a stop. So when the train want to come to a stop, you see the acceleration will be pointing in the opposite direction. To slow down, right? To slow down, so velocity will decrease. When the train comes to a stop, there is force applied to the train, but then the girl, right, she will want to continue moving forward. Okay, she will want to continue moving forward. Same thing if you're on a train, the train comes to a stop, right? You will want to continue moving forward. That's why if you never hold tight, right, you may fall forward. Okay, so this is an illustration of first law. Okay, any questions on first law? First law is more of a qualitative concept. Okay, so we need to know that there is no calculations based on that. Qualitative means it's just explaining and based on words. Quantitative means there will be numbers and of course equations. Okay, so that brings us to second law, which is quantitative. A lot of calculations, right, will be based on this second law. Okay, so actual definition, it states that time rate of change of momentum of a body is equal in both magnitude and direction to the force imposed on it. If you are um, doing physics for the first time, right, this whole statement will seem a bit foreign to you because at this point we haven't learned the concept of momentum yet. Okay, we haven't learned the definition of momentum, but no worries. For now, right, we will have a more simplified version of second law. Okay, so it is said is a quantitative description. So the simple definition of second law, right, you all can just remember it as second law means F equals to ma. Whenever we say Newton's second law, we are saying F equals to ma, where F is force and A is acceleration. Okay, so force equals to mass times acceleration. This is the SI units. Dimensional analysis, you will tell that it's this one. But for forces, right, when we write the units, we write in newtons. Came from his name now. Okay, so Newton will be the units of force. If a body has a net force acting on it, it is accelerated. So this is just trying to describe this equation. Okay, if a body has net force acting on it, it's accelerated. If you look at this equation, right? If there is a positive value, if there's a value for F, M is constant, right? Our mass all always stay the same. So if there is a positive value for F, means there must be a positive value for A. Correct? They are related. Then conversely, if a body is not accelerated, there is no net force acting on it. Also, same thing is trying to describe this equation. It's trying to say if A is equal to 0, then F will be equal to 0. Okay, so second law, just remember it is F equals to MA. This is just a very simple example to illustrate F equals to MA, okay? So imagine we have a car here, 1000 kg. That's about a Toyota Vios or a Honda Jazz, around that mass. So let's say you want to accelerate forward by 0.05 meters per second square. How much force do you need to apply? We know the mass, we know the acceleration that we need. You will just use F equals to ma, you will get the answer. Okay, so this is just to show how F equals to ma is used. But of course, the questions that we are going to deal with, right, it won't look like that. This is too simple. It's just to illustrate F equals to ma. Okay, so we move on. Weight is a force. We know weight, right? We all know what weight is. So weight is actually a force. Is what we are studying now. The force exerted by Earth on an object is the weight of. So just now we learned F equals to ma, correct? So if you look at this form, right, weight equals to mg. So it's actually in the same form. F equals to ma, but when we look at weight, right, the acceleration that we are dealing with is actually g. Okay, so you see it's actually in the same form. Mg is actually ma also. Weight is a vector acting downwards towards Earth. Weight depends on geographical location. So different place, right, on Earth will have slightly different weight because gravitational acceleration is slightly different. But as we had discussed, we will assume g, which is gravitational acceleration, will be the same, okay, around close to the surface of Earth. We will be using 9.8. But weight will change. It is not an inherent property of a body, unlike mass. Mass won't change. So whatever mass for that object, right, how many kg, it won't change. Okay. Mass is in kg, weight is in Newton. Okay, so if we say we are 50 kg, right, actually that won't change, right? But outside we have been using the definition wrongly already. We always ask what is your weight. Some people will say 70 kg, 60 kg. Actually, that is totally wrong. But of course, outside we don't go and correct people, right? But that's because that's referring to our mass. If we talk about weight, we need to multiply by gravitational acceleration. Okay, so don't confuse mass and weight. Weight can change or even be zero, but mass always remains the same. Okay, so the main thing from this slide is don't confuse mass and weight. They are totally different things. Okay, for second law, remember is F equals to ma. Okay, of course, later we'll see how are we going to apply that to solve problems. Now we move on to third law. Any questions regarding second law? Anyway, if you all have questions, right, just feel free to type out. Yeah, just feel free to type out. So if you all want to ask anything, I'll assume everything is okay lah. Okay. So now we go to third law. He want us will there be theory in the final exam? What do you mean by theory? Sorry. Will there be theory in the final exam? Okay, so there won't be don't need. So you all don't need to memorize what is first law, second law, third law, this kind of thing. But you all need to know what it is because we need to apply it. So in the exam, right, there will only be questions. Okay, questions are like problems that we have been trying to solve. like your supplementary questions and the examples that we are trying to solve. There will not be questions to ask you define first law. There won't be this kind of question. It will always ask you to calculate something. Okay? Then which you all need to go and use the correct concept to calculate. So in a sense, the theory that you are referring to, right, there will not be any theory tested. Okay? Any other questions? Yeah, I don't have, then let's continue. Okay, now we move on to third law. More like the assignments question. Um, assignment one, right? You are referring to assignment one because assignment two is just like a project. Assignment one, yes and no. So yes, right? Why yes? Because it's also similar. It's questions like that. Ask you to calculate the forces. What is the force in the rope? What is the acceleration of the vehicle? Okay, it will be questions like this. But why no? Because the assignment is a very long question. In exam, right, there will be 7 questions. So it won't be so long. In the assignment, right, one question is very long. You will never finish in half an hour. But in the exam, it is possible to finish one question in half an hour. Okay. Yeah. So let's continue. Anyway, if you have questions, just feel free to continue typing. Feel free to continue. Okay. Third law, it states that when two bodies interact, they apply forces to one another that are equal in magnitude and opposite in direction. Okay, so this one is actually the law of action and reaction. When you apply a force, right, it means that thing that you apply the force on is actually applying a same force back on. Okay, so this is a concept that we need to know to apply to solve problems. So like I said, right, like this entire statement, right, there's no need to memorize. Okay, but we need to know what it means, which we'll be seeing in a while. Concept is used to analyze problems of static equilibrium. We'll talk about that. At the end of this deck of slides, right, we'll be solving a static equilibrium problem. Okay? And that's a very standard kind of problem regarding forces. Newton's third law, it describes forces, and these forces, right, they are real forces. What do I mean by they are real forces? So these are some examples. Let's say you're in a car, you e-brake, correct? You're belted up, so there's a seat belt. If you e-brake and you want to fly forward, right? You want to fly forward. The belt will try to hold you back. Okay, that's what a seatbelt is for, right? So the belt will apply a force onto you. Actually, right, is because you go and apply a force on the seatbelt. That's why the seatbelt exerts a reaction force back onto you that try to keep you safe. Okay, so this is based on Newton's third law. Another example, wall exerts force on swimmer. Let's say this swimmer wants to accelerate to the left. The true action, right, is actually she go and kick the wall. All right, she apply force on the wall. She kicks the wall. But when she does this, right, based on Newton's third law, it means the wall exerts a force onto it. It means the wall becomes like pushing her. So there's a force pointing to the left. Actually, right, so you see, it's this force that the wall is applying on her that will propel her to the left. Okay, actually, that is the case. But whatever she's doing, right, is she's kicking the wall. Okay, so this reaction force, right? This is a reaction force. This is the actual force. This is a reaction force. This reaction force, right, is actually a real force. Okay, it's not some imaginary force. Some students, when they study third law, right, they think this is just a imaginary concept, but it's not. Okay, so these reaction forces, when you draw out the opposite force, right, it's actually a real force that is doing some real work. Okay, for example, this one, the wall is actually pushing the swimmer to the left, and it actually will bring the swimmer to the left. Okay, it's a real force. Table exerts reaction force on the book. So if you place a book on the table, there is weight going downwards. Right, the weight is pulling the book downwards. But because the book is applying a force on the table, right? It also means the table is applying a force back onto the in the opposite direction. Okay, and it's because of this reaction force. That's why the book stays here. Okay, when the book is on the table, you see that it's at rest, right? Of course, if you go and put a book on the table, it will just stay there. The next morning, it's still there. There's weight pulling it down, right? But why the book is still there? It's because of this reaction force that is counteracting the weight. Okay, these two forces, they will cancel out, so there will be no net force. That's why the book will stay there until someone going to apply a force to move it out. Okay, so reaction force. Another example, the force Fa on B, when we write like that, right, means force exerted by A on B. Okay, exerted by object A on B is equal to magnitude 2 and opposite in direction to the force B on A exerted by object B. So simply put it, right, let's say this illustration here. A is the foot, B is the ball. If A wants to kick the ball, right, you will apply a force here, Fa on B. That means A apply on B. That's why the force is pointing in this direction. But when you go and do that, right, it means the ball is exerting a force on the foot as well. If you kick the ball very hard, right, it's almost like the ball is hitting your foot very hard. So you will feel it, right? You really feel that your leg, or if you never kick properly, you'll be pain. That's why when people play soccer, maybe some of you like to play soccer, you realize actually your head can get quite pain. Okay, so if you're not a professional, maybe don't hit the ball. Okay, last time in school, I have a friend. He plays soccer. Right? He's not in the soccer team, so he just hit the ball. Maybe he doesn't know the correct technique. So after he hit the ball, right, he, he really don't feel well, and then he went to the hospital. Okay, so it's because of Newton's third law. Okay, when you hit something, means that thing is hitting you. Example, another example, illustrating a man pulling a block with a rope. So this is the case. There's a man pulling a rope which is tied to a block. So he's trying to pull the block. So there are two sets of action-reaction pair that we can see here. First set is actually, okay, we look at the red one first. That means we look at how the man interact with the rope. Okay, the man is trying to pull the rope to the right side, which means the rope is trying to pull the man to the left side. Okay, so this is an action-reaction pair based on Newton's third law. The other side, the rope is tied to the block, correct? The rope is trying to pull the block to the right side. You can see down here, I'm looking at this part now. The rope is trying to pull the block to the right side. But at the same time, this block, right, is trying to make the rope stay in place. It's trying to pull the rope back to its position, which is pointing to the left. So this is another action reaction. Newton's third law is about action reaction. Okay, so these are action reaction pairs. For Newton's third law, right, there's also this thing, this concept of the normal force or normal contact force. It's a type of reaction force. That's why we will learn it when we learn Newton's third law. Okay, it's a kind of reaction force. For objects on Earth resting on a surface, it's pretty much almost everything. But we all rest on a surface. For example, an object on the table. The normal force balances the force of gravity and provides equilibrium. So this is about the same situation that I've described just now, correct? So when there's a weight point pulling it down, and because it's resting on the table, there's a reaction force pointing upwards. These two forces cancel out and provide equilibrium. So what is the normal force? When these forces are perpendicular to the ground, they are also called a normal force. Or rather, when they are perpendicular to the surface that they are on. Okay, maybe ground is not a very good word. Okay, maybe surface that they are on. If they are perpendicular to the surface, then we call them a normal force. So in this case, you see the book is resting on the table, right? The table is, the surface is here. And then now the force is pointing upwards. This force is perpendicular to this surface, correct? So this reaction force, we will call it the normal force. It's just a definition. We continue with normal force. The magnitude of the normal force is not necessarily equal to the magnitude of gravitational force. Just now remember the book on the table, right? We see that the reaction force is same as the weight. Both same, that's why cancel out. But it's not all the time that it must be equal to each other. So for example, when one object pushes downward on another object with force F, the normal force N is greater than the force of gravity. So let's say this is the same book, right? It's on the table. Fg is the force gravitational force caused by gravitational acceleration, which is also the weight. Okay, this is the weight. Because this person, right, going to push down with additional force. So now not we don't just have the weight holding it down. We also have this person like trying to push it down. Okay, so when the normal contact force act, right, it will be bigger than the weight already. It must account for the weight and also the force that the man applied. Okay, so it may not necessarily be equal to the gravitational. Normal contact force is just the contact force when it's perpendicular to the surface. Reaction force that is perpendicular to the surface. Okay, so any questions regarding third law? If not, then we'll take a look how to solve a very standard equilibrium kind of problems regarding forces. So before we solve, we will briefly go through what are the steps that we are trying to do, okay, to solve this kind of problem. First, we will draw a neat, simple diagram of the system to understand more about the question. Okay, sometimes questions, right, when they ask you, it's just in text, there's no drawings. So you must draw a neat, simple diagram to help yourself. But most questions in exams will have a diagram to help you, or to assist you to get what it's talking about. But if you don't have, then you have to draw a simple diagram. Next, we isolate each body being analyzed, and we draw this thing called a free body diagram showing all external forces. Later, we will see how to draw this thing called a free body diagram. And as mechanical engineers, right, you must be very familiar with this free body diagram. You will use this concept when you study mechanics throughout. Next time when you do mechanics, even fluid mechanics also, when you analyze, right, it's also based on a lot of free body diagram. Third step, we establish convenient axes for each body and find the component forces along this axis. Convenient axis, we write convenient here, but usually convenient means x and y. But not all the time. That's why we don't put establish x and y, because sometimes the most convenient one is not x and y. Okay, but most of the time it will be x and y. After we do that, we apply the Newton's first law, second law in component form. That means, in other words, we'll most of the time apply F equals to MA to try to see how to solve it. Next step is solve the component equations. After we apply, right, equations will come out. So we will try to solve it. Ensure that you have as many independent equations as you have unknowns. As we know in mathematics, if we have the same number of unknowns as equations, we know problem can be solved. So for now, we will assume objects are point masses. Remember, when we assume objects are point masses, right, that means we neglect rotation. Because point don't neglect. Point don't rotate. Sorry, point don't rotate. For example, water, we will treat it as a point. A car, we also treat it as a point. So this is the assumption. We neglect effects of friction unless specified. So in this topic 4, right, there will still not be friction, but later on we will introduce friction, as we will see in the next topic. But actually, friction is just another force. We will just neglect it for now, so that we study the most simple thing. Neglect mass of ropes involved. So when we see ropes, chains, or string, if they never tell you the mass, right, we will assume that These kind of things like strings, they have no mass because they are too light already, so we can neglect. When Newton's laws are applied, focus only on external forces that act on each body. External forces are like forces from the outside that is trying to push or pull the body. Okay, let's say I'm holding this pen, I'm actually applying force on the pen. But internally, right, maybe the molecules they are holding each other, right? They are internal forces, but we don't care about this kind of internal. We only focus on external ones. Okay, now let's take a look at this example. Car engine in equilibrium. A car engine with weight W hangs from a chain that is linked at ring O to two other chains fastened to this one fastened to the ceiling and the other to the wall. So this diagram on the right, it illustrates what the question is trying to talk about. So one chain is here to the ceiling, this is to the wall, and then there's this O-ring before there's another chain and then holding this engine. So this whole thing, if you place like that, right, it won't be moving. When things don't move, right, it is in equilibrium. Okay, but you can imagine there will be forces inside all this. Okay, find the tensions in each of the three chains, assuming that W is given. W means the weight of the engine. So assume the weight of the engine is known already of a certain value. And also the weights of the ring and chains are negative. So they tell you these chains, all these three chains, right? And this O-ring is massless. So assume that they have no mass. Because this engine is so much heavier, right? So we can neglect the masses here. Tensions, when we talk about tension, right? Tension is actually a force. Okay, for chains, ropes, and strings, similar matter, right? Something that extends and hold other things, there will be tension inside, which are actually forces. Okay, so if question asks you to find a tension, means they're asking you to find the forces in one of these things. For example, string or chain. Okay. So how do we find the tension in the three chains? The top part here is just rewriting out the question. So this is the diagram, and then find the tension in each of the three chains. They tell you W is known. W is the weight of the engine is known. So first step, we need to isolate different bodies in the question. Okay, we need to isolate different bodies. Then we draw out the free body diagram. The first body that has useful information, right, for us to isolate is this engine. When we isolate the engine, you imagine making a cut on here. Okay, imagine making a cut. So yeah, the T1. So imagine you make a cut across. Imagine you're cutting the chain. Okay, cut. So you cut already, right? Then you look at the object that's below, or rather the body that's below whatever you cut. You want to draw out the free body diagram of that thing. Okay, that's called isolating something. Okay, so when we isolate, we draw the free body diagram, which is already drawn here. We assume there are points, right? So you will just draw a point. Up to you, like you want to draw out the whole engine also can. Maybe some of you that you're drawing very nice, right? But then you will just draw an object in the middle. Then now you will label the forces that is acting on the body. Okay, this particular isolated body. So you ask yourself, what are the forces involved? First thing, there will be a weight pointing down. Okay, this thing is hanging, right? There is gravitational force pulling it down. So you will draw an arrow pointing down, and then usually we label W. They stand for the weight. And then there's also a chain here. Okay, whenever you make a cut across chains or strings, right, you expose the forces inside. In this chain, there will be tension. You can imagine if you pull the chain very tightly, this chain will be super taut. Correct? It will be very tight. Those are tension inside, but when you see it, right, what we feel is the chain will become very tight. Okay, that means it's in tension. For free body diagram, we won't be sure whether it's in tension or the opposite. When it's the opposite, right, we call it compression. Tension versus compression. But for free body diagram, we will always assume that it's in tension, which we will, from the object here, we will draw an arrow pointing outwards. Okay, from the object. We will always assume in tension. when you are wrong, right? Let's say this string, right? This chain here is actually opposite. It's actually in compression, right? You'll realize after that when you solve for this T1, you will get a negative value. That will tell you your assumption at the start is wrong. But from conventions, right, we will usually assume intention, which means from the object, we will draw an arrow pointing outwards. And then we label T1, which stands for tension 1. Okay, so this is the first free body diagram that we will have. Next thing, we will go and isolate another body so that we can get more equations later. Okay, so the useful part for us to isolate will be this O-ring. So you can isolate this O-ring. When you isolate the O-ring, what you do, again, you will make cuts around it. Okay, so when you isolate the O-ring, that means you make, imagine you make a cut here, make a cut here, and make a cut here. Okay, so you're left with the O-ring with 3 exposed chains, all right? So you will go and draw a free body diagram for that. O-ring with 3 exposed chains. So you expose the tension, right? We always assume tension. So from the body, we will draw the arrow pointing outwards. Okay, so you see the bottom chain here, down here, we draw arrow pointing downwards. Just now you draw upwards, right? Never mind. When you draw outwards, right? Outwards as in outside, point away from the body. That means you are assuming intention. So this one point outwards, this one also point outwards. That means you are drawing correctly. Okay, always point outwards to assume tension. So we draw outwards, assume tension. Same for T2, we draw outwards, assume tension. T3, the same direction as where it's supposed to point because there's a 60 degrees here. So you draw T3. Okay, so by right, we are supposed to have 3 forces, right? Up till now, T1, T2, T3. But do you notice something? T1, T2, and T3, they are not in very nice 2 directions, right? In the previous lesson, when we solve problems, we would want to make everything go into 2 directions so we can sum them up together. So down here, same thing, because forces are vectors as well. So we will want the forces to nicely fall onto 2 directions only. Okay, so the easiest way to make these 3 forces go into two same directions is we go and resolve this T3 into one pointing in the y direction and one pointing in the x direction. Okay, so how do we do that? We know this is 60 degrees based on this. So the one pointing to the right must be T3 cosine 60. T3 is the hypotenuse, T3 cosine 60. And then the upward force will be T3 sine 60. Okay. So now we can see we have 4 forces, right? T1, T2, then this T3, we already break it up into one going upwards, one going to the right. Now we have 4 forces, nicely on x and y direction. Then we are settled on this drawing diagram part already. We can move on to the next step, which is to write out the equations. How do we write out equations? We will want to take summation of forces to apply F equals to MA. So this first equation here is based on the first free body diagram. We take summation of forces in the y direction. So you see y direction, there's only T1 going up and opposite direction of W. So you will sum them up. T1 minus W, that's our F, right? Right side, you know y is equals to 0. We are applying F equals to MA here. Okay, this is our F, but right side is 0 because the acceleration is 0. Remember this whole thing, it is not moving, right? So acceleration is 0. In this context, you will ask yourself, you are summing out in the y direction, right? Is this object moving up and down? No, right? The answer is no. So it's not accelerating up or down. Okay, so right side is 0. Based on this equation alone, you already solve for T1 rate. Okay, so T1, the tension in T1, right, must be same as the weight. The force that's pulling it down is causing the same tension inside. Okay, then you solve for T1, now you have T2 and T3 to solve. So you continue, you look at the other free body diagram, you can take summation of forces. We do y direction first, so summation of forces in the y direction. We have T3 sine 60, positive y, right? T3 sine 60 minus T1. So we write out T3 sine 60 minus T1. Then equals to what? So we ask ourselves, now this O-ring, right, is it moving up and down? It's not, correct? That's why equals to 0. Okay, so from here, you will get an expression T3 equals to something T1. Okay, so we cannot solve it because you have two unknowns. But never mind, you continue. You move on. Now with this same diagram, you continue to take summation of forces in the x direction. So look at x direction, what do you have? You have T3 cosine 60. You also have T2 in the opposite direction. Okay, so you minus T2 equals to 0. Same thing, why 0? Because the MA, right, is not moving left or right. Okay, so 0. From here, you will be able to solve. Okay, 3 equations, 3 unknown. You confirm can solve for all. T1, T2, T3, you will all get answer. Remember here, W is not unknown. W is a known. Okay, it's known. So in this manner, when we draw free body diagram and then we take summation of forces, we can solve for all the tension inside the chain. Okay, so we know all the forces inside. Okay, any questions? So this is quite a standard way of solving static equilibrium problems that involves forces. When we deal with forces, right? Questions that deal with forces, it is very likely you need to draw free body diagram. Almost quite standard one. When you have forces involved, right? The first thing you should think of is free body diagram. Okay, try to know the forces acting. Okay, so in this manner, we solve for the tension inside. Of course, this is a simple question. But for example, let's say you're an engineer, right? You're trying to design this system that can hold an engine. Let's say you're in the car workshop. You need to know the tension inside the string, right? So that you know which chain will break first. And then you need to design that chain well enough you can hold the weight. Okay, so from T1, T3, T2, for example, this simple problem here, you see T3, right? Is holding the most tension. That means there's most force inside. Okay, it's 1.155 of W. So if anything, right, this T3 will break first. Okay, so you need to design this T3 to be able to hold the weight. Yeah, just for um, some understanding, like why do we solve this kind of thing? Yeah, if no questions, then we move on, and then we continue drawing more free body diagrams. Next example, what is the grading of the spring balance? Neglect masses of spring and string. So assume frictionless surface. Down here we have this illustration here. They ask you what is the reading. So we have an object like that, right? What do we need to do? We have to go and draw the free body diagram. Okay, so this is the block. Then you ask yourself what forces are acting on the block. First one, almost quite standard. You always have a weight pointing down. As long as we are talking about objects on Earth, right? Always have an object pointing straight down. Then you're right, either W or mg, because weight is mg. Up to you. Okay, you just label it, and then because this object is on the surface, there will be a normal contact force perpendicular to the surface, like this orange line here. There would also be a force. In this case, there will be this spring balance, right, which is trying to hold the block right towards its direction, which is the tension that we want to solve in this case. Okay, which is the tension that we want to solve in this case. So now we have three forces, right? The blue, the red, and the orange one. They are not in very nice directions. Realize? So you have to make it to go to very nice directions. And from this example, right, you can see why x and y may not always be the most convenient axis. Okay, so for an object on an inclined slope, you see the most convenient axis will be one along the slope and the other one that's perpendicular to it. Okay, that will be the most convenient one. If you try to resolve everything into x and y, That means you resolve this to x and y. You also resolve it to x and y. You will also be able to solve it, just that you make life difficult for us. Okay, so usually on inclined slope, we won't do that. We're going to resolve this mg to two components, one along the slope, which is mg sine theta, because you know theta is here, right? 30. When 30 degrees is here, means 30 degrees is here. Okay, let me draw. If 30 degrees is here, means the 30 degrees will be here. Okay, our geometry. Okay, that's why this is mg sine theta, and this is our mg cosine theta. Okay, then to solve the question, right, they are just asking you what is the reading of the spring balance. That means they are asking you what is the force of this red one. If you take summation of forces in this direction along the slope, right, you'll realize this T must be equals to mg sine theta. Okay, because it must cancel out, right? The block is not moving. So this T must be equals to this. That's all. You don't really need to care about the other two actually. Okay, so you find T is mg sine theta, and then you will solve what this question is asking for. Okay, then next example, tension in elevator cable. An elevator and its load have a total mass of 800 kg. The elevator is originally moving downward at 10 meters per second. It slows to a stop with constant acceleration in a distance of 25 meters. Find the tension T in the supporting cable while the elevator is being brought to rest. So an elevator looks like that. There are cables on top which will have tension inside. They tell you the scenario is originally moving downward at certain speed, and then it slows to a stop with constant acceleration at some distance. So if they write like this, right, actually it's a sort of a hint, right? They need you to use kinematics to solve for something first before you continue with the next part of the question. Okay. So for this question, right, they give you all this info is to let you find what is the acceleration. Okay, so you look at the info that you have, slows to us. This is the initial velocity, original, right? Initial, then slows to a stop. That means the final velocity will be zero. So that's another info. And then all this happens in 25 meters. So we have three info. To find the fourth one, confirm can find. So every time when given three, right, you can always find the fourth one. Depends on what you want to find. Okay, so in this case, you want to find the acceleration, so we can apply F equals to ma, right? That's why we want to find the acceleration. We'll apply this equation here. V square equals to u square plus 2as. Okay, this is from the equation. You put in all the values and then find what is the acceleration. Okay. Then for the free body diagram of this question, this dot is the leaf. What are the forces acting on it? There is a weight pointing downwards. Correct. And then the cables, imagine you make a cut in the cable, right? You expose the tension. Okay, that's why you draw away from the object. Then that's it. There's only these two forces acting on the leaf. Then outside here, right, there's an acceleration pointing upwards. You all know why upwards? Because it's originally moving down, right? Imagine you're in a lift. Now you're moving down, reaching the first floor already. To stop it, right, your acceleration needs to point upwards. Okay, that's why the acceleration going upwards. So from here, you'll be able to apply your F equals to ma. But F, there's only T, there's only W the other side, so only two forces. You will just have T minus W equals to ma. Now this ma, you don't anyhow put zero already. Okay, it's not all the time zero. Because in this question, right, the A has a value. Okay, A has a value. So from here, you will go and solve for your T, okay, which is the tension. So this is the tension in the cables. Okay. Then there's also this thing called the apparent weight. Same as the previous example, lah, okay, is also in a lift kind of thing. Sometimes you feel that your weight can change, right? You feel heavier standing in an elevator that accelerates upward and it moves towards a higher floor. If you have a bathroom scale at the time, the scale will show that you are heavier. But are you actually heavier? I'm sure all of you know this, right? When you go and take lift, when you start to accelerate upwards, you feel that you are heavier. Then when the lift tries to stop, right? When you reach the higher floor, you try to decelerate. Then you will suddenly feel lighter for a while. Okay, so we can feel that the weight can change, but of course it's not changing. Okay, that's what we refer to as the apparent weight. So if you draw a free body diagram, right? Let's say down here, you're looking at this scenario. Let's say you are here, you're accelerating upwards. The forces you have, right, is actually the weight pointing down, and also because you are the leaf, right, the surface, there will be a reaction force pointing upwards. Okay, so actually the summation of forces, this one here is referring to this one, this case. The other case, never write out. So this one here is referring to this case actually. Okay, so you take R minus mg must be equals to ma. So if you shift things around, right, and then you find out what is R, it will give you R equals to mg plus m. This R, right? Yeah. Okay. So this R that we are looking at is actually the apparent weight that you feel. Okay, so you can see here is actually your real weight, then plus this MA component. So if you accelerate very fast upwards, right, this A, if you get very high, right, you will feel that you are being pressed into the ground, right, into the ground, the floor. So you'll feel that you are very heavy. For the other case, when the acceleration is downwards, it's actually, if you go and draw the free body diagram, it's mg minus ma. So if you accelerate downwards very fast, right, you'll feel yourself becoming very light. Of course, the most extreme case is when you accelerate so fast that this ma, right, cancel out this mg. That means you won't feel anything really. You are essentially like falling down, right? Like free fall. Like. Okay, so this is the apparent weight that we are feeling in questions. So the next few slides, they are all supplementary questions for yourself to read. Okay, if with no questions, then we'll move on to topic 5. Okay, before a break. Topic 5. Wait, this us the elevator mg plus ma. The m is mass of elevator or human. It's the mass of the human. Okay, because we are analyzing the human inside. So the human, right, is actually our free body diagram. So the m, right, always depends on which object that you are isolating. Okay. Yeah, good. Okay. Yeah, good question. Okay, so no other questions, then we move on to application of Newton's laws, part one. Right, just now it's already on Newton's laws. Now we go to part one. In this part, right, actually is about the same thing, just that we add friction to it, okay, to the bodies that we are talking about. Just now when we draw the free body diagram, there's no resistive force on, right, no friction. But in real life, actually there's friction trying to stop the object. When a body moves on a surface or through a viscous medium, for example, air, which we are all in, or water, there are forces of friction because body interacts with its surroundings. So when we move through air, right, or water, or move along a surface, right, there will always be this friction trying to stop us. There are two kinds of friction. One is the static friction. We'll denote using Fs like this. This is the force that counteracts the applied force and keeps the object from moving. So this Fs, right, if we draw a Fs, then for static friction, the static part, this friction force is when the object is not yet in motion. Kinetic friction is the same thing, it's also friction force, but it's present when the object is in motion. So imagine you want to push a huge box. Imagine you have a huge box beside you, very heavy. You try to push it, but it still hasn't moved. Correct? You already apply force, but why never move? Okay, when haven't moved yet, that means the friction that is trying to stop that is a static friction. It is there when it's not moving yet. Okay, but let's say you keep applying force, then suddenly, right, you overcome that already, and then the object is moving. The object, the box that you are pushing is moving. You apply a lot of force, but the object moves very slowly. Okay, but it's already in motion. That one, right, the friction that is trying to hold you back, right, is Fk, kinetic, okay, because it's already in motion. So the difference is one is when it's not moving yet, the other one is already moving. Concept of friction force. Fs increases as the magnitude of the applied force increases, keeping the object in place. So like I've said, like a box, right? This one on the right, this is a diagram to show the friction on the y-axis. Down here is across time. Okay, so down here there's a slope, right? It means over time you try to apply more and more force, more and more force. Okay, but this part, the object still is not moving yet. So this whole part, we are in static friction. Okay, we are in static friction. Then there will come a time where you will reach the Fs max. This is the point where the friction cannot hold the object in place any longer. Okay, when it's on the verge of moving, this Fs will reach the maximum. When this applied force exceeds this value, Fs max, the object will start to move. In other words, the object start to accelerate. Because the force that you push overcome this Fs max already. Okay, there will be net force. Net force. Net force positive, so the object will start to move. Once the object is in motion, the friction force will change to Fk. We are no longer talking about static anymore, because static is for not moving. After that, it changes to kinetic. And this is a behavior that is almost all the case. So almost everything that you try to push, right, you try to start, right, you will always reach a point, then when it starts moving, it will drop a little. Okay, this Fk will be a lower value than the Fs max, usually. Okay, then after that, it will remain somewhat constant. But you see the dagger line here, right? It's because when you see it from a micro point of view, the surfaces, because machining cannot be perfect, right? So there will be jagged edges, which will not make it move so nicely. Okay, but of course, when we look at things from a macro point of view, we can assume this to be a straight line. Assume to be a straight line. So when it drops a little, it will mean the applied force, the force that you're trying to push, right, will be quite a lot more than this Fk. Because you already apply until this Fs already, right, your force match this Fs. Suddenly when move, right, the friction force drop a bit, but the force that you are applying is still around this level, correct? So there's a difference between the applied force and the friction force. So object will start to move based on that. Empirical laws of friction. So this is just a formula for friction. So whenever we are dealing with friction, right, we'll be using these formulas. The direction of the force of static friction between any two surfaces in contact is opposite the direction of any force and can have values this one. So two things. One thing is friction, right, always act in the opposite direction of motion. If you try to push a box to the right, friction confirm will act to the left. Okay, because it's opposite direction. It's always trying to retard your movement, trying to slow it down. And what is the value that you can have? The magnitude is given by this. So Fs must be smaller or equals to mu s n. Mu s is the coefficient of static friction. It's almost like a constant between two surfaces. We always have this coefficient. N is our normal force. Okay, N is our normal force. Remember just now we talked about normal force? This is that normal force that we are talking about. Okay, this is for Fs. Then for Fk, exactly the same thing, plus that the mu s become mu k. So now it's coefficient of kinetic friction. If you take mu k times the normal force, you will get your friction force, kinetic friction force. Fs and Fk won't exist together. So friction force, right, is either Fs or Fk. When it's moving already, right, then Fs will disappear already. It's not based on Fs anymore. It will be based on F. Okay, so it won't be appearing together. Coefficients of friction, so the mu s and the mu k that we are talking about in the previous slide, they depend on the nature of the surfaces. These are the typical values. We will not need to memorize any of them. If needed, right, it will be given. But mu k is generally smaller than mu s. Okay, mu k is generally smaller than mu s. That's why just now in the diagram, right, we see there will be a small dip. Okay, because mu k in general is smaller than mu. The coefficients of friction are nearly independent of the area of contact between the surfaces. That's a characteristic. Although mu k varies with velocity, we normally will neglect this. Okay, so usually we won't care about this. We will assume that mu k is constant. Then these are examples of materials and their corresponding mu s and mu k. Okay, so you see the values are usually is below 1. And yeah, they can have very different values. If they are very small, right, it means there is very low friction on these materials. One thing interesting one is if you go and look at rubber or concrete dry, rubber or concrete wet, you can see for static friction, it from it is on a value of 1, then when it rain, right, it drop to a value of 0.3. Okay, so friction now when we have wet weather, it will suddenly drop by a lot. If you drive, yeah, drive maybe cannot feel it because we don't go and drift around. If you cycle, right, if you anyhow cycle and you have anyhow take turns, you turn very fast, right, on wet roads, you will feel that you will skid very easily. Okay, because the coefficient of friction drop by a lot from dry to wet. And then also in general, you compare mu s and mu k, right? They are about the same, but mu k is usually slightly lower. Mu k is slightly lower, except for some materials. So naturally occurring materials, right? Usually mu k lower. But these days, scientists they will engineer new materials, correct? They can create characteristics that they want. So for example, Teflon, you see everything the same. Teflon on Teflon, Teflon on steel, you see the mu k and mu s, they are all the same kind of coefficient and very small value, very slippery. And you know what is Teflon? Teflon is the material that you see on your non-stick pan when you fry dishes, you fry egg, right? The black color part there is Teflon, so very slippery. Okay? So mu s and mu k is the same, right? That means the Teflon When you go and rub it and you try, right, and you go and put water, then you rub it again, right, you should feel about the same. Okay, so about the same, and of course they feel as slippery as each other. Like they need to be slippery so that things will. Okay, so this is just some general values which you don't need to memorize. Now we look at this part where um, the coefficients of friction are determined. So how do they determine these coefficients of friction, right? It will help us, this derivation will help us to solve problems also. Not that we need to know how they derive, but the way they derive, it also is the way that we can use to solve problems. Okay, same angle, same forces. So let's go through this. Suppose a block is placed on a rough surface, inclined relative to the horizontal. The inclined angle is increased until the block starts to move. So imagine this box, right, actually is flat one. Then they go and increase this angle, right? Keep increasing this angle. So it will get more and more inclined. Then there will be this angle, right? This critical angle, whereby the block will start to move. When it starts to move, right, that angle is associated with the coefficient of static friction. But you break off the static already. So that value, right, is associated with this mu s. Later we will see what is the equation that's involved. Okay, but this value is associated with the static part. Once the block starts to move, it accelerates down the incline. So continuing from the scenario, so when it reaches the angle, it will start to accelerate downwards. Accelerate, that means it will speed up. However, when that happens, if theta is reduced to a value less than theta c, it may be possible to find an angle such that the block moves down the incline with constant speed. So when you reach that critical angle, it will move faster and faster, right? Then at that point, you go and reduce this angle. It will reduce by a bit. So you will reach the point where there is no more acceleration. Alright. It will only move at constant speed. No more acceleration. That is the point that we want to find, and then that is the angle that's associated with it. That means when you find this angle, right, means forces cancel out. And that is associated with our mu k. Okay, so this is roughly the idea behind how they find the coefficients. But how about the equations and what's the angle for? How do you relate to it? Okay, it's based on this free body diagram on this slide. So if you go and draw a free body diagram, right? A block is here. Same thing. First force you always will draw is a mg, weight pointing downwards. And because it's on the incline, there will be a normal force perpendicular to the surface. And in this case, remember this topic, suddenly we have another force coming, right? Come inside. It is the friction. Since the block is moving downwards, or it is expected to move downwards, the friction will point in the opposite direction. Okay? Friction always act in the opposite direction. So we have three forces essentially, one mg, one is n, one is f. Okay, so the next step, same thing, you see these three forces, right? The directions don't look friendly at all. So you have to make all the forces point towards two directions only. And same as our previous topic, the easiest way to do it is to resolve this mg into mg sine theta and mg cosine theta. Okay, mg sine theta is the one along the slope. Okay, so after you get this, right, it's almost like there's four forces. So this one disappear already, right? This mg. Almost like this mg disappeared. So now you have four forces. You already resolved it already. So now we can take summation of forces. First, we look at the x direction. Now we define the axis like that. You see a bit singing, a bit tilted. Okay, because this is the most friendly direction. So let's say this is the x direction along the slope. Take summation of forces. We have mg sine theta minus f. Okay, that will give you a ma. And since it's not moving, not accelerating, right side is 0. Okay, so that's the first equation. Second equation, take summation of forces in the y direction. That means like this, the y direction. So y direction, right? We have n. Okay, we have n here, and then we have also mg cosine theta the other side. That's why we will take a negative. And also a is 0, okay, because it's not accelerating in the direction. So now we have two equations. We want to combine them. The way to do it is to put it into this form. Okay, so if you look at the top equation, you make fs the subject. If you do that, the right hand side you will end up with this sine theta. Same thing for the equation below. You make n the subject. The bottom here, right, you will end up with mg cosine theta. When you see sine and cosine, right, the best way to combine it is to combine it into tangent, correct? Because we know sine over cosine equals to tangent. Okay? So we will go ahead and take the top equation divided by the bottom equation. Okay, so if you do that, you're going to get something like that. This sine cosine become tangent. This one is actually fs over n. But go and put it the other side. The n already bring up. Okay, then this fs here, we will substitute with the friction formula, which is our mu s n. Remember the previous few slides, mu s n is the formula. So if you substitute then that in, the n will cancel out. The n will disappear. You'll be left with mu s equals to tangent theta. So you see this expression here, right? Mu s equals to tangent theta. If we know the angle, just now remember we tilt the angle up and down to see how the block moves, right? This critical angle, right? If we know, right, we just do a tangent of the angle, right? We will know the coefficient of the object really. Okay, so whatever we have analyzed here, this whole thing, the top is for static part. For kinetic part, right, exactly the same free body diagram. That's why it's not written out. Exactly same steps also, you will end up with exactly the same question. Just that the angle is the angle that we are talking about, the new critical angle. That's why there's a prime here. So this is when you tilt the slope a bit backwards, to find a constant speed at time. Okay, you reduce the angle. Okay, any questions so far? Yeah. So no questions. We continue. We take a look at an example. A 2 kg block is placed on top of a 5 kg block like this. The coefficient of kinetic friction between the 5 kg block and the surface is 0.2. So we're talking about this surface here. Between the 5 kg and the surface. So we are talking about this surface. Okay, it's 0.2. Coefficient of kinetic. Part A, calculate the force needed to pull both blocks with an acceleration of 3 meters per second squared. Okay, we do this part A first. So part A, the whole system is like that, right? And we want the whole system to accelerate to the right, 3 meters per second squared. So forces are involved, correct? First thing you do, usually go and draw the free body diagram. So the whole thing, take it as one object. First thing you have a mg pointing downwards. You can write mg here. Down here they write 7 kg, same thing. You just need to know this is the force, right, due to gravitation. So it will become 7 times 9.8. That will be the mg. Then because it's on a surface, you have a normal force pointing upwards from the surface, which is unknown at this point. You have to go and calculate. Another force is your Fk, because you are pulling this to the right, is moving to the right, correct? The friction that will be acting will be to the left, so you must draw a force pointing to the left. Okay, so there are 3 forces. And from here, you will try to find what is F required. Of course, this F you must draw because this is the force that you are pulling, right? You are pulling the object, so the force must be there. So you must go and find what is this F. Okay, so step by step, you'll be finding that. First thing you need to calculate is this N. You already know the mg pointing down, and in this direction, right, there's only N and mg. So naturally, you will know that this N, it has to be your mg, correct? It has to be your mg. So you will take a 7 times 9.8, you will get your answer for N. This is a normal contact force. Then, once you find a normal contact force, you will be able to find the friction force already, because remember our friction formula is mu kn. Mu k is given, N we have just found it, so you will take mu k times your N, that will give you your friction force. So this Fk that is trying to trying to pull our motion back, right? Trying to stop our motion, right? It's 13.7 Newton. Now that we know what is Fk, right? We will look at the horizontal direction because we want to find F. So you'll take summation of forces in the horizontal direction. So we'll take summation of Fx. There is only F pointing to the right, and then minus Fk is here. Okay, pointing opposite, that's one minus. Then F must be equals to MA, right? So the whole M that we are talking about, the mass of the entire thing, is M1 plus M2. Then this A is the acceleration that we require, which is 3. When you write out this equation, right, you realize F is the only unknown, which is what we want to solve. Okay, so we need to have a force of 34.7 newtons. If we pull this whole thing with a force of 34.7 newtons, right, this whole object here will accelerate to the right with 3 meters per second. Okay? Okay, Muhammad Mirza asked whether can explain on the last part. Okay, so the last part I assume is this summation of forces in x direction, right? Okay, after you find the friction force, this part, after you find this already, you will take a summation of forces in the x direction because this is what you ultimately want to find, correct? This capital F, which is along the x direction. So you will just take a summation of forces in the x direction, which only you will go and look at what forces you have in the x direction. You only have this capital F, so we write capital F here. And then the other direction, right, you have a small fk, which is the friction, and it's in the opposite direction, correct? So there will be a negative sign. If F is positive, means Fk is negative. Okay, they must be in opposite direction because friction always acts opposite. And then the right hand side will be your MA. So we ask ourselves, what M are we looking at? The body that we are isolating, right, is the whole thing. That's why M in the MA, right, must be 7 kg, must be the whole thing. Okay, then A we also know because the question asks us to find this, right, this scenario where A equals to 3. So you will sub 3 inside. Okay, then after this step, you realize this capital F is the only unknown. You will go and solve for a capital F. Okay, then you will find your answer. Okay, yeah, understood. Okay, good. So we move on to part B. Yeah, no problem. So part B, find the minimum coefficient of static friction between the blocks such that the upper block does not slip under this acceleration. So this part here, right, they ask you to find the minimum coefficient of static friction so that this thing, when you pull to the right, this thing won't fall off. Imagine you have a block below, right, and a block at the top. In real life, imagine if you go and pull the bottom block so fast, right, with a lot of force to the right, what happens? this 2 kg block will start to want to fall back, right? Correct? Want to fall back. So what is preventing this 2 kg block from falling back? It is the friction that is between the surface. If there is enough friction, this 2 kg block will not fall backwards. It will continue to the right with a 5 kg block. Okay, so because of this friction, right, that's why they ask you to go and find the minimum coefficient of static friction between the block. Okay, so that's what's supposed to happen for part B. So now we are looking at the top object, right, and the surface, which is the 5 kg block. So we will isolate that body and then draw free body diagram based on that. Okay, so this is the top block. Free body diagram, what do we have? Same thing. First thing you draw, right, pointing down, always have your mg. Okay, this is your mg. You write 2 kg, but know that this is your mg based on 2 kg. Okay, and then because it's on the 5 kg block, it's on the surface, right? So there must be a normal contact force that is pointing upwards. In this case, it's labeled as N1. Okay, then what other forces are there? You know that there's friction, right? So we need to write a friction force. But do note the direction of the friction force. Down here, right, when we pull the bottom block forward, this 2 kg block will tend to want to move backwards, correct? Relatively to this block. You will want to move backwards. So the friction that is trying to stop that, right, is actually pointing forward. Okay? You can also see as this 2 kg block wants to move to the left in this case. It wants to move to the left. So the friction must be pointing to the right. Okay, so actually is this friction that is trying to accelerate this 2 kg block together with the 5 kg. So we need to have enough friction. Okay, so with this free body diagram, then we will continue solving. We take summation of forces in the y direction to solve for your normal force. For friction, usually we will try to solve the normal force. You know why? Because friction, right, the formula has a normal force component inside. We try to solve for our normal force, okay, which is equals to mg. This is m, this is g. So we have the normal force ready. And then we know friction equals to mu Sn. Okay, in this case, it's mu s, not mu k because it's not moving yet. So it's mu Sn. Then we will solve for mu s. Okay. So you can see after you draw the free body diagram, usually it takes summation of forces and then we will try to continue solving. If friction is involved, usually we will need to do something with the normal force. We need to probably solve it. Then we can use this friction formula put inside. Okay, and then try to solve it. Any questions? If not, then we continue regarding resistive forces. So friction is also a kind of resistive forces. So when we say resistive forces, right, it's actually more general. Okay, it's more general. It's forces that is trying to resist our motion. So interaction between moving object and medium sometimes cannot be neglected. The medium exerts a resistive force F on the object opposite to its direction of motion. So you can see from this statement, right, actually friction is also a resistive force. When you put things through a rock into water, right, there will be resistive force acting on the rock also to try to slow down its motion. Magnitude of the resistive force generally increases with increasing speed. The actual dependence is complicated, so common approximations we will use like this. Okay, so this is a bit into fluid mechanics already. Okay, but they are roughly the same concept, is resistive forces. So for small objects moving at low speeds, right, when we are looking at low speeds, we will have it's just F proportionate to V. K is a constant. K is a constant. So resistive force proportionate to velocity. It is proportionate to speed. But if it's a high speed, right, high speed like a plane and a race car, all this, right? The force will be proportional to velocity squared. So high speed is a lot of resistive force, wastes a lot of energy, because it's to the power of square. When to use V, when to use V square, right? It's until now still very unclear. There is so these are all approximations. These are all very complicated. Even researchers they are still studying now. Okay, but when we approximate things, right, it's already accurate enough for us to use. Okay, so imagine this velocity, right? If you times two the velocity, if you times two your speed, right, you can see that the resistive force will increase by 4 times, correct? Because 2, when you times 2 here, there's a square, becomes 4 times. So when you are driving at very high speeds, right, actually you're wasting a lot of energy. Yeah, a lot goes into overcoming this resistive force. So people who drive very fast, actually they burn a lot of fuel, okay, because of resistive forces. This is the free body diagram that we are talking about. Okay, there will be a weight pointing down, resistive forces pointing opposite. So if you draw up the summation of forces, we do it out, it will be equals to MA. A is also is dv over dt. Remember, this is the differentiation velocity with acceleration. So it's just another way to write it. Okay. Then since F equals to kv, we can change the equation to look like this and then move things around to get this expression here. We won't be testing you on how to solve this now, okay? This is a ordinary differential equation, but because our focus is not on mathematics, we just want to know how things behave. Now we are studying how things behave based on the equation, but we won't actually ask you to go and solve this kind of complicated equations. Okay? So this is the equation that describes the motion. And then it's from here, right, that we can learn about this thing called the terminal speed of velocity. When v equals to 0, that means velocity equals to 0, the resistive force is minus kv. The resistive force minus kv is also 0. Okay, because based on this equation, right, if v is 0, this is acceleration. dv over dt is acceleration. When v equals to 0, acceleration is simply equals to g. Okay, so imagine down here is you drop object down, free fall. So you from here, you accelerate downwards, right? So at the starting point, v equals to 0, so acceleration equals to g. As t increases, the resistive force increases and the acceleration decreases. As t increases, that means as time passes, the velocity becomes a certain value, right? And it becomes bigger and bigger. So when velocity increase, you see there's a negative term here, right? So this acceleration will get smaller and smaller and smaller. Okay? Until there will be one point, the velocity gets so huge that it totally cancels out the g. Okay, that means at that point, acceleration becomes 0 already. Okay, when acceleration becomes 0, means this object that you throw down, right, is traveling at a constant speed. That's the max speed that you can get already. That speed, we call it the terminal speed or the terminal velocity. Okay, so that free body diagram that we draw, if you take summation of forces, right, we equate to 0, you will be able to find the terminal velocity of the object. So this is the equation that we have just now, right? And then say don't need to solve. Okay, basically this is our first order ordinary differential equation. ODE means you see there's a dv dt, right? But in the same equation, there's also another v. It's like you have a y in the equation, and then there's also a dy dx. Okay, our ordinary differential equation. So a solution for this, right? This equation will be given by this. So if v equals to this expression over here, there's a e to the power of something. this is actually an answer to this. Okay, if you solve it, this will be one of the answers. But we just want to write here to plot out to see the behavior, okay, with resistive forces. If you plot this out on a graph, right, it will look like this. Okay, the dark green line with fluid resistance, because there is a component, this component, e to the power of something. Okay, so you can see with fluid resistance, if you go and drop something, right, it will approach this terminal velocity, cannot exceed, right? Okay, because there is a resistive force that is increasing, trying to slow it down. As compared to no fluid resistance, remember last week, we drop things, it will almost accelerate for as long as possible. Okay, that's when there's no fluid resistance. For air drag at high speeds, just now we say, right, air drag at high speeds, F is proportional to V squared. But these equations, right, they are all just approximations. All just approximations. So we will use whichever approximations that we need. So just for example, because they are all approximations, right? So if you take approximations from different scientists, right, the free body diagram, it will end up with different, uh, different expressions. So you see this terminal velocity given by this, another terminal velocity given by this. Okay, because all these studies, right, they are very empirical. For exams, right, if if you are asked to solve this kind of question, right, we will tell you what to use. But then this this air drag part, right, is unlikely to come out. Unlikely to come out. Okay, because we are more focused on mechanics, not so much on the fluid mechanics part. Okay, but it's the same concept. Okay, so to continue looking at graphs, right, compare with and without resistive forces. So typical projectile motion, remember that last week we talked about projectile motion. If there's no air drag, it will be a very nice tall curve. But with air drag, right, it will become shorter. Because at every point of time, right, there will be forces trying to slow it down. So it will be shorter height, it will end up closer. Okay, and just now, these are the acceleration, velocity, and your position graph. Because now we have seen this already. If you draw the one for acceleration, right, it's going to look like this. With fluid resistance, the acceleration will go to zero after a while. Starts from G, then you will go to zero and you drop something. Same thing for position. No fluid resistance. In a same amount of time, you can see this way, same amount of time, it's going to travel further with no fluid resistance. But with fluid resistance, right, it's going to travel to a shorter distance, okay, which is of course logical. Right? Okay, any questions regarding friction? So this topic 5, right, actually very similar to topic 4, just that we have this another new concept, this new force come out, right, which is friction force. But the free body diagram and the summation of forces actually is the same. Okay, so if you just treat friction as just another force, actually it's the same thing. Okay? The concept of solving forces, problems regarding forces is the same. Always about free body diagram, then you take some of forces, and after that you see how you want to solve it. Okay, any questions? If no questions, then maybe we take a short break. We come back 8. Yeah. Hey, why you have a? Can I know what is N? As in which slide? I assume it's This slide, right? What is N? We're talking about this N. Okay, this N is a normal contact force. So for questions involving forces, right, when objects are placed on a surface, you see they are all on a surface, right? When they come into contact with a surface, when you draw the free body diagram, there will always be a normal contact force perpendicular to the surface. This force is like the surface, right, exert this force on the object. Okay, because the object is resting on a surface, right? So this N is actually the force that the surface apply onto the object. That's why the object never go through the surface, right? There is a force trying to stop it there. Okay, this is the force applied by the surface on the object, and it will be perpendicular to the surface. This surface is flat, that's why it's like that. If it's inclined, this N will be inclined that is such a way that is perpendicular. Okay? Yes, it is a reaction force. So it is a reaction force, but you don't really see it from gravity because it may not be equals to your mg. May not be. Okay, it's just a force that arises because they're in contact. Remember just now I said if you go and press down the book right on the table, the normal contact force actually can be big. Okay, so it is a reaction force, but it may not necessarily be the same as your gravitational force. Okay, good, good. You're welcome. No problem. Okay, so if no other questions, then maybe we continue at 8:35. Yeah, 40 minutes break, 8:35. Then for attendance, right, you all just stay in this chat. Okay, just stay in this chat. I will mark based on whoever is in this chat room. Okay, just stay in the chat can already. I mean, device wise, you stay in the chat lah, but you can go and take a break. Okay, so see you all back here 8:35. Okay, yeah, thanks. Okay, yeah, Takashi, see you later.
I'm passionate about so many things.
There's nothing I won't do. When you sound the alarms and the chaos is rising, leading the charge, I'm coming, I'll fight and swear on the breath that I breathe, I'll never retreat, yeah, I'll be your arm. Yeah, we said we let it go, but we settled for the last. Couldn't let you want it though. Who am I to let you down? No. Who am I to let you down? Down, if you let me walk away, maybe then we'd lose it all. No. Who am I to let you hold me close till I get up? Combing your hair with your hand gives me feelings I don't understand. Combing your hair with your hand gives me feelings I don't understand. You do this thing when you're biting your lip, it's driving me crazy just looking at it. You know me better than I know myself. I don't wanna live in a world without you. You do this thing when you're biting your lip, it's driving me crazy just looking at it. You know me better than I know myself. I don't wanna live in a world without you. World without you. Driving me crazy just looking at it. World without you. Driving me crazy just looking at it. You do this thing when you're biting your lip. World without you. Driving me crazy just looking at it. Driving me crazy just looking at it. Combing your hair with your hand gives me feelings I don't understand. Combing your hair with your hand gives me feelings I don't understand. You do this thing when you're biting your lip, it's driving me crazy just looking at it. You know me better than I know myself. I don't wanna live in a world without you. You do this thing when I'm talking to you, like everything freezes and it's just too. You do
Okay,
this
hello
thing when I'm talking
everyone.
to you,
Welcome
like
back.
everything freezes and it's just
Can you hear me?
you do
You
this
all
thing when
still
you're
can hear
biting
me?
your lip, it's driving me crazy
Okay, good.
just looking
Thanks.
at it. You know me better than I know
Okay, so
myself.
now we'll be going through topic 6 and 7.
Give it to me like
I hope can end before
world
10:30.
without you.
Okay. Anyway, this lecture so long, right? So I hope before 6:30 you all have time for dinner. If not during these 20 minutes, go and get a quick bite. If not, have to eat very late supper. Okay, now we come to another new part of Newton's law. We are talking about circular motion now. Remember when we study kinematics, we also talk about circular motion, right? When things travel in a circle, there is this radial acceleration or centripetal acceleration. And then we saw that the formula is v square over r. So this v square over r, this is just a recap. This v square over r, right, this radial acceleration is directed toward the center of a circle. Okay, and ar is always perpendicular to v. V is our velocity. V is tangential to the circle, right? That's why AR will be perpendicular. So now, right, that was the kinematics part. When we study Newton's laws, we want to involve forces. right? Same thing, right? Involve forces. So we will be applying F equals to ma to that motion. Okay, so for the circular motion, if we're going to apply F equals to ma, it will look something like that. The ma, right? The a is the radial acceleration, and we will be able to sub v squared over r into that formula. Okay, so it becomes Fr, this is radial force, will be equals to mv squared over r. A force causing a centripetal acceleration acts towards the center of a circular path and causes a change in the direction of the velocity. So if you see the diagram over here, velocity is always tangential, right? You see at this point is tangential, this point tangential. Then the acceleration due to this circular motion, because of the fact that it's moving in circular motion, we have this acceleration pointing towards the center of the circle. Okay, then the force must also be pointing towards the center of the circle. This force and this acceleration, right? This F and this A, right? We're talking about the radial component. That's why they are in the same direction. Okay, you also can see as the velocity actually at this point, right, is traveling in this direction, right? But you want to change the direction such that it will move to its left, correct? So the force that you apply to this particle will to its left. You also can see it that way. So at every point, right, you are always driving it to its left, such that it will appear to be traveling circle. Okay, so F equals to mv squared over r. Let's look at an example. A pendulum bob of mass m is suspended from a thin wire of length L. The bob moves in a horizontal circle with constant speed v. So this is the illustration. Horizontal circle means the gravity is acting downwards, as in it's not speeding up the motion. Okay, it's just a horizontal circle. Okay, so it hangs from a string, right? Then you displace slightly, then you move it in circles. Okay. So the gravity don't play any part in trying to speed it up. That's a horizontal circle. With the wire making a constant angle beta in the vertical direction. Down here. Find the tension F in the wire and the period. So tension, now they use F. Usually we use T, correct? But tension is also a force, you can use F. But why now they use F? Because T, right, they also want you to find the period, which is the time to go one round. So it's a force question, right? There's force involved. So you have to draw a free body diagram. So this bob, right, you imagine you take a cross section of it. You imagine it's moving in this circle, right? Then imagine the ball is here, let's say right at one end. Then you take a view from the side. Actually, you take a snapshot, right? A camera snapshot, side view. You will end up with this free body diagram. So this is the bob, and then there will be a string, right, going upwards. Okay, so that bob you are trying to draw a free body diagram. So the first force you have is always a weight going downwards. And then there's a string here, right? There's a string here. So you will be drawing a tension force there. We will assume tension. So same thing, from the object point outwards, you label your tension. This question is F. Okay? And then the bob is trying to move in a circular motion at that time, because remember we take a snapshot side view, right? So actually this bob is trying to move in a circular motion like this. Of course, you cannot see a circle from here. You only see a line, right? It's moving in circular motion because you are looking on the side view. So the radial acceleration is pointing at this moment is pointing towards the center of the circle. Okay, because the circle is here. It's moving like this. So this will be it, and then there will be a beta this angle. Okay, so same thing. These two forces, right? They are not in two friendly perpendicular directions. So you have to go and resolve the forces. The force to resolve here is this F. You want to put it into along the y direction, and along the x direction. Okay, so following three goes same thing. F cosine beta, this will be F sine beta. Now, it's as if we have three forces. One is this F cosine beta, one is F sine beta, and the third one is your mg. Then here, right, you will take summation of forces. So in the x direction, you have F sine beta. That's the only force, right? So that force will be equals to your ma. Because it's pointing towards the center of a circle, right? So the a that we are talking about is your radial acceleration. That's why we have this mv squared over r here. Okay, because equals to ma, this radial acceleration is actually a v squared over r. So this is for the x direction, the equation. Y direction, which is this one, we have f cosine beta, then minus mg, because mg is in the opposite direction. Okay, then that's all two forces only, right? So two forces, then the right hand side equals to ma. But you ask yourself, is the board moving up and down? It's not, right? It's not moving up and down. That's why the ma down here is 0. There's no acceleration in the y direction. Okay, so with that two equations, now you can solve for what you need to solve for. So in the question, they ask you for F, tension, and T, which is the period. For tension, right, you can see actually from the second equation, you can already solve for it. Down here, you shift mg to the right side, and then divide by cosine beta. Actually, you solve for your F here. Okay, but how to get the period? The time taken to go one round. You need to make use of both equations. Any simultaneous equation. Okay, so there's a sine, there's a cosine. So same thing lah. The best way is to take the top equation, divide by the bottom equation. Sine divided by cosine, you get tangent. Down here, you must shift mg to the right first. Okay, before you can divide. So the bottom equation will look something like f cosine beta equals to mg. Okay, so this equation, f sine beta equals to mv squared over r, you divide by f cosine beta equals to mg. So you see, this sine beta divided by cosine beta, you get tangent, right? Then this f cancel out. Then on the right hand side, you get mv squared over r divided by the mg. Okay, that's how you get this. Tangent beta equals to v squared over rg. Okay, and down here you can further express it in terms of length of the string. Okay, because the radius of the circle, we know the length of the string, right? Imagine the length of the string, and we also know the angle. Of course, we can write in terms of the length of the string. If this r change to L sine beta, this one. So this is L, right? R, we are talking about this. Okay. So you can see this L and this R, right? Actually, it's just a triangle. So we are talking about triangle here. R, right? You can easily change it in terms of L beta. Okay, that's what they are doing here. Next step, they make V the subject, velocity the subject. So this expression is for velocity. To find period, right, which is the time taken for one round, we take the distance for one round, which is 2 pi r, that's our circumference, divide by velocity. Distance by velocity, you'll get the time taken, right, to go one round. Okay, so if you divide, you'll get this expression here. Of course, it will still stay as an expression because this problem never give numbers, right? We want it to live in terms of this alphabets. Okay. Yeah, no questions, then we continue into another example, negotiating a curve. A car is rounding a flat unbanked curve, radius r. if the coefficient of friction between tires and the road is mu s, what is the maximum speed Vmax at which the driver can take the curve without sliding? So imagine you are a car driving. You are a car driving. You want to turn right. As you turn right, the turn can be described as a circle with radius r. Okay, the moment you turn a vehicle, a particular turn at an instant, right, it can be described as a circle with radius r. Okay, it's just if you turn very slightly, right, of course the circle is super huge. If you like U-turn, if you make a U-turn, then you turn very sharp. You can imagine the circle will be quite small. Okay, so in other words, as long as you turn, there will be this radius of this imaginary circle. Okay, and that's radius r. So you turn right, correct? You will feel that you want to move to the left. Okay, the car will want to skid to the left. So what is stopping the car from not skidding to the left is this friction between the tires and the road. And friction comes with the mu s. Static friction, because the car hasn't skid to the left, the car maintains its grip. So if you look at this, right, the car is not moving to the left, it's not skidding to the left. So the friction is static friction. Okay, because the car hasn't slid yet. What is the maximum speed at which the driver can take? Okay, so if you travel faster than this Vmax, you will start to slide to the left. So they ask you to find that. So how to solve this question? Same thing, forces involved, right? We always must draw a free body diagram. Okay, so this dot is the car. We always have weight pointing down. Okay, Michael asked, will these formulas be given during our exams? Some yes, some no. So the formulas that will be given, right, is in the formula sheet. You can go to your canvas to see the formula sheet. It should have been uploaded by the course coordinator. Okay, so that formula sheet, right, that will be what you'll be given. So those that are inside, then it will be given to you, and you can refer to that. Okay, so some alphabets, right, represents the same thing, but may not be. Remember, I told you in the first lesson, different people write different alphabets to represent different things. For example, sometimes U is initial velocity, but sometimes V naught is also initial. So as long as you know all this, right, you know the concepts, you can interpret the formula sheet very well. Confirm, no problem. Okay, yeah, no problem. For anything, can just ask me. Okay, so we continue with this problem. Forces, right? So first thing, free body diagram. This is the car, and by now you should know that you always have a weight pointing down. Things on the earth. Okay, and because it's on the surface, right, on the road, so there will be a normal force perpendicular to the road pointing upwards. And you have another force here, the friction. Okay, it's this friction that is trying to prevent the car from sliding outwards. You turn right, you will tend to want to go left, correct? You want to go left, but you are not sliding outwards. So the friction is helping you to prevent that. Okay, so the friction is pointing in the opposite direction. That's why friction must be pointing to the right. Okay, so the friction is actually pointing to the center of the circle. Okay, at this point, the acceleration you must know, because you are moving in a circle, there will be a radial acceleration. So with knowing all this, with this free body diagram, then it's time to take summation of forces. So summation of forces in the y direction, we have n minus mg equals to ma, which is 0. Because this car is not moving up or down, right? So right hand side equals to 0. Summation of forces in the x direction, we only have F, which is the friction force. The F, right, must be equals to ma. So because we are moving in a circle, in that direction, there is actually a radial acceleration. We are moving in a circle. The force that is pointing to the center, right, is actually your friction force. Okay? And it is in the same direction as a radial acceleration. That is given by v squared over r. From this mv squared over r equals to F, the F, right, you can change. This is the formula for F, friction. Remember, friction is your mu Sn. Then N is your mg. Yeah, so friction, the formula is mu Sn. Then from here, we can see that N equals to mg. Okay, that's why friction will be mu S mg. Okay, so from here, you want to find what's the V max. Actually, you just make V the subject. You can get an expression for it in terms of mu S, which is the static coefficient, and also depends on how much you turn, is the radius of curvature. Okay. Anyway, for the formula sheet, you can take a look first. Then we will go through the formula sheet in the last lesson. So lesson 6, we will just go through the formula sheet. Then I'll tell you, oh, this one is learned from this chapter. That one is actually which one is okay. We will go through the formula sheet in the last lesson, so you are more familiar. But of course, if you are damn very good, don't need formula sheet also can. Okay. Okay, he was n is always the y-axis. No, cannot say it's always the y-axis. But when objects are on a flat ground, like this, on a flat ground, because n is perpendicular to the ground, to the surface, right? So it happens that objects that are on a flat surface, the n will be in the same direction as up or down, which is y. Okay, so it happens to be like this because it's flat ground. I think in the next example, we will see n is not along the y-axis. Okay, so next example, I think next slide or next two slides, so you can see already. Okay, but to continue this part, so Vmax, this is the maximum speed that you can get. It depends on your static coefficient, that means how much friction you have, and also radius of curvature. Okay? So if your radius is super huge, that means you turn a bit only, right? You can go at higher speed. That's what this expression is trying to say. And if you have a lot of friction, you also can go at higher speed without skidding. Okay, so this is, if you have values, you put it, you will get value for V. Okay. So now we go to another question, which is similar but different one. Now we are negotiating a bank curve. When we say bank curve, that means there is an angle. There is an angle. The curve exit ramp is to be designed for highway in such a way that a car will not have to rely on friction to round the curve without skidding. Maybe some of you would have noticed maybe you take car or taxi along the express, right? If it's from for example, our CTE to PIE, right? You take the exit, right? You will realize actually there is an angle to it. Okay, the angle is to help us not to skid outside. Right? Okay, of course, it must be angled in this manner. If you angle in the other way, you will kill the driver. Okay, you must be angled in this manner, okay, to help us not to skid outside. But very minimal, okay, very, very minimal. Usually just a few degrees at most. So such a ramp is usually banked. Suppose the designated speed for the ramp is to be 25 meters per second and the radius of the curve is 230 meters. At what angle should the curve be banked? So down here, you want to take this curve again. So very similar curve. But you will want this angle here. They ask you what must this angle be, such that even if this road is super slippery, no friction at all, totally no friction, you still can go this curve without skidding outside. Okay, that's what this question is asking about. So for this, right, the free body diagram, if you draw it out, analyze the car. First thing, same thing, gravity still pull the car downwards. Which direction will hardly ever change. Okay, as you draw a bit funny. Okay, you point downwards. Okay, wait, directly downwards. Then you see this car is on the surface and now it's not flat already. Okay, so normal contact force will always be perpendicular to the surface. That's why you see this normal contact force is drawn at an angle. Okay, at an angle must be perpendicular to the surface, like this. Right? So that's why I hope this answer your question. A1. Just nice. The next question answer the question. So n, right, may not always be aligned to the y-axis. It is always perpendicular to the surface. If there is an inclination, right, then n confirm off up and down the axis rate. Okay, so down here we have two forces, and of course they are not perpendicular. So the first thing that you need to do, right, next thing you need to do, you need to resolve one of them to make it perpendicular. So you resolve this normal contact force to point in y and x nicely. Okay, you have the angle here, which is beta. Okay, then after that, same as the previous question, this radial acceleration, right, points to the right, points to the center of the circle. Okay, then armed with this free body diagram and whatever you've drawn, right, you take summation of forces in two directions. One is x. X, you have n sine beta, and that points to the center of the circle, right? So that will give you the MA, which is radial acceleration. We point to the center of the circle. So the right hand side will be mv squared over r. Summation of forces in the y direction, you see what you have. You have n cosine beta. You also have mg pointing to the side. So you will take n cosine beta minus mg, because mg is in the opposite direction. And right hand side equals to 0. This is your MA, because you ask yourself whether the car is traveling up or downwards. In this question, it's not. So acceleration in the y direction is 0. Okay, then these two equations, you combine them together. So take the top equation, divide by the bottom equation. Cosine divided by cosine, you get tangent. This mg, imagine you have already bring it to the other side. So exactly same as the question just now. Okay, then you will get p squared over gr. So down here, you will be able to answer the question already, because they ask you to solve for beta, right? Given a speed and some radius of the curvature. So you will sub in these values, 25 meters per second, and 230 meters, right? You will be able to get your beta. Okay, so for this particular speed, 25 meters per second, and then turning this much, right? Radius of curvature 230. If this car go through this curve where the angle is 15 degrees, the driver don't even need to rely on friction at all. Okay? So imagine if it's on ice, you also won't skid, because everything is balanced out for him not to move outwards. The other can explain again how to combine both equations. Okay, sure. Okay, so there are two equations, right? These two equations, you see sine and cosine, right? Actually, it's a hint that you can combine using sine over cosine equals to. Okay, but first you have to make sure both sides fit quite nicely lah. So left hand side divided by left hand side, right hand side divided by right hand side. So the bottom equation, right? You see, you should make it in this form. So bottom equation should become something like N cosine theta equals to mg. So you shift the mg to the other side. Okay, correct? Top equation is already in the correct form, but let me rewrite to make it look not so confusing. Top equation is actually n sine beta equals to mv square over r. Now, you take the top equation, you take this whole thing, and then you divide by this whole thing. Left hand side, divide by left hand side. Right hand side, divide by right hand side. Can, right? Okay, left hand side, this n will cancel out because we divide. Sine divided by cosine, get tangent. Right? You get tangent. Right hand side, you will take mv square over r divided by mg. So it will become like mv square over r divided by mg. Okay? Then of course you will get this. Okay, good. No problem. Okay, so everyone else, yeah, any more questions? If no questions, then let's continue with another example. So on circular motion, a pilot of mass m in a jet aircraft executes a loop-the-loop. It is a maneuver. So in this maneuver, the aircraft moves in a vertical circle of radius 2.7 kilometers at constant speed of 225 meters per second. This is very fast, meters per second. Usually, in fighter jets, this kind of speed, like normal for them. Determine the force exerted by the seat on the pilot at the bottom of the loop and at the top of the loop. So this is the maneuver. They can travel in a vertical circle. So down here, right, if they fly upwards and then they continue to fly steering in that manner, right, they will go upside down and then they can come back down. Okay, so this is a vertical circle. So we are asked to find out at the bottom and at the top, what is the force exerted by seat on the pilot. That is actually the normal force now, okay? So at the bottom, you draw the free body diagram. The pilot, free body diagram of the pilot. So the pilot will have a weight going down. And then because he is pressing onto the seat, right? The seat exerts a normal contact force on him. Okay, the seat exerts a normal force on him, which is in opposite direction, pointing upwards. It's at the bottom. At the top, right, he is upside down. Mg is still pointing down. Okay, Mg always point down. But now since the seat is up here, right, he's in contact, correct? The normal contact force the seat is exerting on him is pointing downwards now. Can you see? Now he is below. The seat is at the top. So he is sitting on the seat, right? So the normal contact force is pointing downwards. So if you write out the summation of forces for the bottom, it will be n bot minus mg, so mg in the opposite direction, equals to mv squared over r. Because at this point, you are traveling in a circle. Okay? That's why it equals to mv squared over r. Same thing, very similar. Okay, for the top, you write the same thing. Down here, the both form point towards the middle of the circle. Okay, this is when you are here. This is when you are here. And this is when you are here. Okay, so when you are here, you see the forces point downwards, right? At the top. The forces point downwards means the forces point towards the center of the circle. Okay, so that's why these two forces, when you add up together, equals to MA just nice it is pointing towards the center of the circle, right? So it's also mv squared over r is positive value. Just now, n board, you take this to be the positive, right? A minus mg. So the overall direction you are taking is pointing upwards. Imagine you are here. So you take this to be positive direction. That's why just straight away apply mv squared over r on the right hand side. Okay, because it points towards the middle of the circle. So down here, if you make the normal force the subject, push it to the left, you can see the normal force is very different when he's at the top and at the bottom. Okay, down here is what he feels. Normal contact force is what he feels, a reaction force, right? He feels a lot more because it's this same term but plus one. Okay, that means he really feels that he's being pressed onto the seat a lot. But when he's at the top, he doesn't feel that he's pressed into the seat that much. There's a minus here. So you take some value off. There's a minus sign. And logically speaking, that should be correct because you're at the top, right? Gravity is pulling you down. So you shouldn't feel that you are pressed into the seat as much as at the bottom. Okay, so one is uniform circular motion. Uniform circular motion, again, is constant speed. Constant speed. Now we are moving to non-uniform circular motion. Non-uniform means it is not moving at constant speed. Okay? It's still circular motion, but now not moving at constant speed. That means when it's moving in this circle, right, it can accelerate or slow down. Okay? So there will be now additional components because just now when moving in circle at constant speed, right, you only have one force pointing to the middle of the circle. Now, because you can speed up or slow down, there will be a tangential force also. It's this tangential force that's trying to speed or slow down. Okay, so it's a vector. So vector addition will work like this. Same for the acceleration. Force and acceleration, they are both vectors. This example here, an example of non-uniform circular motion. This is a mesh round a vertical circle. Round a vertical circle means the plane, right, is in the vertical direction. So if you go and swing a ball in a vertical direction, there will always be mg pointing downwards, right? So you can imagine at some points the mg is trying to accelerate it this here. But if you're at the other side, the mg is trying to slow it down. So the speed at any point is not constant. So this is the example. A small sphere of mass m is attached to the end of chord length r and rolls in a vertical circle about fixed point O. Determine the tension in the chord. So same thing, at this point, you just choose a random point, you draw a free body diagram. So same thing, there will always be mg pointing down, and because there's a string, so there's a tension. There's tension, and then they are not in nice directions, right? We make them go into nice and perpendicular directions. So you will resolve this mg into mg cosine theta and mg sine theta. So it's as if now you have three forces. Right? So it's as if now you have three forces. Okay, so here you are going to take summation of forces in that two directions. Of course, for this question, they ask you to determine tension in the chord. That means find this T. Find this T. You just take summation of forces along this radial direction, right? You will be able to find it. Okay, so summation of forces along radial. You have T. You also have minus cosine, minus mg cosine theta. And this is towards the center of a circle, so you have mv squared over r. Let's make T the subject. We'll be able to find the tension in the chord. And based on that equation that we've gotten, right, the expression, some interesting cases again is at the top and at the bottom. Almost like the airplane pilot. Okay, at the top and at the bottom, you have different tension. Okay, so you want to know the tension at the top, right? Sub theta equals 180. If you want to know at the bottom, you put theta equals to 0. You get two different expressions for it. So you see tension at the top is negative. There's a minus sign here. Tension at the bottom is a positive sign. So when this thing swings at the bottom, right, when it's at the most bottom point, the tension in the string is the highest. It's much higher than at the top. Okay? So if you really whirl in a vertical circle, right, the string, if it's going to break, it's going to break first objects at the bottom because down here experience very high tension. Okay, so the rest they are all supplementary questions for you to have a look. Any questions regarding circular motion? Basically, is circular motion that we have learned, but now apply the F equals to ma onto that system. Okay? With no questions for now, let's go into topic 7. Right, we are moving into another new, not really new, another um, another kind of different topic. Okay, not forces, not focus on forces anymore. Of course, forces will still appear. It's on energy. Okay, let's move into that. Okay, I move to 7. It's on work and energy. So 7 and 8, they are both on energy. Today we'll do half of it. Half of the energy is 7. Okay. So for work and energy, right, we will start to revise this about the scalar product first. I'm sure you all have learned before, but let's do a quick revision because the work done that we are talking about, right, for the energy is actually based on scalar product. So scalar product of any two vectors A and B is denoted by A dot B. When we say A dot B, we are talking about scalar product. The other kind is A cross B. Right now we're talking about A dot B. A cross B will revise next time. So now talk about A dot B. It's a scalar quantity which is given by this formula here. Okay, we call it the dot product. This whole line here is just describing the formula. So don't need to worry too much. Okay? So we need to know A dot B, these are vectors, is actually equals to AB cosine phi. Phi is the angle between the two vectors. So if you have A here, B here, the angle between is phi. To get the value for A dot B is magnitude of A times magnitude of B cosine. The actual definition, right, is actually the product of the magnitude of A and the projection of B onto A. When we say projection of B onto A, that means you see B is here, right? B is here. If this B, you project like a shadow like that, project it. If you take a light and shine top, you project onto A, you will get B cosine phi. Okay, so it's actually A times this projection. That's why AB cosine phi. But just remember dot product as AB cosine phi. Some properties of dot product. Scalar product, dot product is commutative by normal multiplication. It also obeys the distributive law of multiplication. So if you have a bracket like this, right, it will work like this, same as normal multiplication. But the special properties of scalar product, right, is this one, the third and the fourth point. A dot B will be equals to 0. A is perpendicular to B. Okay, so if it's perpendicular, it will be 0. Why? Because if you put back into the formula, right, if it's perpendicular, the angle will be 90, correct? And cosine 90 is equals to 0. That's why A dot B will be 0. The other scenario is A dot B will just be the magnitude of A and B if A is parallel to B. So if they're in the same direction, because same direction, that's why angle 0. When you do a cosine 0, that is the max that you can get, 1. Okay, so it's equals to the magnitude. So because of that, if you dot something in the same direction, right, if you dot yourself, right, I dot I in the same direction, right, 1. But if you go and another unit vector in another direction, right, no matter how you dot, because they are perpendicular, so always come to 0. Scalar product of two vectors, if A is given by this and B is given by this, as ij, k components, different components, if you do a dot B, it's actually easier than normal multiplication. Okay, you see this whole thing, right? You dot this thing. You will just need to take the first one times the first one down here, then plus the second one times the second one, and plus the third one times the third one, finish it. Okay, so dot product multiplication like this, right? Actually easier than normal multiplication. Okay, so this example here is just a math example, simple math example for you to recap dot product. So find the angle between two vectors. So let's say vector A, vector B. They are in 3D as you can see, it's IJQ. If you look at the illustration, it's something like it. They ask you to find the angle in between. Okay, so we can make use of the dot product to help you solve this question. Okay, to make use of dot product, first you're going to find the magnitude of A, is the Pythagoras theorem of the 3D form. Find the magnitude of A. Magnitude of B, same thing, Pythagoras theorem. Also, you know A dot B, right? Remember we talked about how to do the multiplication. A dot B, easier than normal multiplication. You just take first one times first one, second one times second one, plus third one times third one. When you do that, you will come to a value. It's just a scalar. Okay, that's why it's called a scalar product. There is no direction to it, it's just a number. So with this and this, you can put into this scalar product formula here. As you can see, you already have this. You also have this. You also have this. Right? All you have to do is to find what is this phi here, which should not be a problem. So you can use dot product to find angles between vectors. Okay. So now we come to energy. Why we revise scalar product? Because actually work done, right, this energy is based on scalar product, which we see. So some intro to energy first. Classical mechanics, most of the mechanics that we are doing, concepts of work and energy, they are very important. They are based on Newton's laws. So if you use forces or if you use energy, right, they will somehow come to the same answer. Right? You can solve them using both methods. Okay, they will agree with each other. It can be applied to dynamics of a mechanical system. It's useful in complex situations, for example, variable forces. So remember forces, when we draw free body diagram just now, right? We always draw a force, and then the force we assume to be a fixed force rate. Let's say the force is 30 newtons. We just take it as 30 newtons. So, but what we have a scenario where the force keeps changing on. Now we push with 30, later we push 35, after that we reduce 25, but we still push in the direction. but you still continue pushing. So the force keeps changing. You cannot solve using force methods really. You can use energy methods to solve it, okay, which you will see. So useful in complex situations and applicable to the right range of phenomena. Energy is present in various forms. For example, mechanical energy, which is moving things, mechanical energy, electromagnetic energy. This is something to do with electricity and magnetic waves. So for your induction cooker, all this, right, it's based on this. Electrical energy, I'm sure you all know. Chemical energy, these are energies that are stored in batteries. Okay, even the AA battery that you see, these are chemical energy. The fuel also, diesel, petrol, all chemical energy, because they are chemical. Thermal energy, this is basically just heat, okay, heat energy. Nuclear energy, also, I'm sure you all know what it is. It's just energy based on nucleus. The second point, energy cannot be created or destroyed, but can be converted from one form to another. This is a very important concept because this gives rise to this thing called the conservation of energy. When energy is converted from one form to another, the total amount in the system remains the same. So energy, right? We study energy, the total energy that a system has, right? It must stay that value. Okay, it cannot be created out of nowhere. And then if energy is lost, right, it must go to somewhere else also. Okay, this is the conservation of energy. For example, car petrol, we burn petrol, right? Combustion, chemical energy. We burn it to produce useful energy for us to move the car. So the part that is moving the car is the mechanical energy. Okay, the energy also goes into electric energy, charge the battery, right? And the battery will power the auxiliary system, your player, your radio, all this. And you will go into heat also. That's why when you stand beside the car, you're outside the car, the engine, all this, right, it gets very hot. The energy goes into heat. But of course, heat is an energy that's unwanted in this case. Okay? But all these are energies that's converted from one form to another. Work done by a constant force. Now we come to work done. Work done is actually energy, okay? Work done by a force, we say this manner means it's force times displacement. So if you have a box here, you want to move it to the right. You apply a force to the right, correct? Then the box will have moved this distance here, rather displacement. So the work done for this particular situation, where you apply this force F and move this distance, it is given by multiplication of 2. Okay, so work done goes to force times the displacement. And work done is actually energy. Okay, so joules is the units for energy. When we talk about energy, right, the units that we want to see behind is always joules. Work done by an agent exerting a constant force is the product of the component of the force in the direction of the displacement and magnitude of the displacement of the force. This statement, right, is just trying to say only the only the component of the force in the direction of the motion is counted. Okay, which is why scalar product is used. So work done, the actual formula, right, is F dot S. That's why it will come to Fs cosine phi. So if it's not in the same direction, right, it's not counted as useful work done. So for example, there's a car, you want to push here, you want to shift to the right. Okay, displacement is to the right, as you can see the arrow directly to the right. But this person, he's going to apply a force that's somewhat to the right, but also upwards. Right? Somewhat to the right, but also upwards. So the work done for this scenario is actually only this component is counted. The F, if you resolve, right, there will be the F cosine phi. Of course, there will be another one. There's another one over here. So this is your F sine phi. But that one, the F sine phi, right, is totally not counted at all. Don't need to care. Okay, we only want to know the force that is in the direction of the displacement. That will go to your work done. That's counted as the work done. So this formula, there is no work done if object doesn't move. Why? Because S is 0, right? If S is 0, means done with 0. And apply a lot of force, but if object never moves, there is no work done to this. There is no work done if force applied is perpendicular to the displacement. We'll see some illustrations later. But essentially, it's saying if the object wants to move to the, if you want it to move to the right, but if you apply work downwards or upwards, right, you use force to apply, also not counted. Okay, because wrong direction. There's a cosine inside here, which will turn that. Work done can be positive or negative. For example, when object is lifted, the work done by applied force is positive because they are in the same direction. When you lift something, when you lift something up, you also apply outward force, it is positive in the same direction. However, work done by gravitational force is negative. So it depends on which force are we talking about also. Let's say I leave this pen, correct? It's going upwards. But actually gravitational force is pulling it downwards. So from the point of view of gravitational force, right? Displacement is going up, but the force is applying downwards. So the work done by gravitational force will be negative. Okay, then here are some scenarios, different scenarios to show what would the work done. The first one, object moving to the right, you push right, right. So both are to the right. So work done, definitely positive. Second scenario, object moving to the right, you apply an angle and an angle. So the force is somewhat to the right and to downwards also, right? Down here. So the force here, we will be taking the force, the horizontal one, multiplied by the displacement. So this one can be resolved to this one, correct? Okay, so it's as if this F is resolved into that 2. So it's one, the one pointing to the right that we are looking at. Okay, but you see, after all, it's still pointing to the right. Direction is to the right. Okay? So work done is still on. If I look at the third one here, the object is moving to the right, but you're going to apply a force to it. So work done will be negative. Okay, different direction. Then the last one, object moving to the right, but you go and press downwards. Okay, the force applied downwards. So as you can see, the force is totally perpendicular to the motion. Correct, totally perpendicular. So if you follow the work done definition, this one work done will be 0. Not positive, not negative, but 0. It's not totally not counted at all. Another illustration, weight lifter, you lift the weight up. So S means displacement, the weight is going upwards. You lift upwards F, same direction, so positive work done. Okay. Then when he lift it up, now you want to maintain it here, right? The displacement is 0, because not moving. But to maintain it here, he needs to apply a lot of force, and you see he's very tired, right? Apply force upwards. In this case, he is also not doing work to the system. Okay, although he apply a lot of force, he is not doing work to the system. He's burning a lot of internal energies, internal energy in his body. That's why he's losing calories. But in terms of the system, which is to move the weight, right? He's not trying to do anything. Okay, because it's not moving at all. In last case, he wants to slowly put it down. Never throw down, right? So he slowly put down. Displacement is going down because he put it down. But because he slowly put it down, right? As the weight go down, he is also applying a force upwards. Do not let it drop abruptly. That's why the force is quite upwards. In this case, you see the force and the displacement different direction. Okay, so there's negative work done. Okay, now we come to some equations and numbers already. Okay, any questions so far? Should be okay lah, huh? Same thing, if you have got questions, just straight away type in the chat. So work done by varying force, how do we calculate that? Just now is work done by constant force. That one force times displacement, very straightforward. But for varying force, you see this is force against distance, right? As it moves, the force also changes. You push with more and more force. So for varying force, consider the work done over a small displacement. So can we say technically push up is only negative work done? Push up as in the army we do that push up. Or are you referring to the weight? Okay. Okay, cannot really see like that also. So we must depend, it depends on which system are we analyzing. So very similar to the weightlifting one. Very similar. So you see, when we lift our bodies up, right, we are pushing the ground, but the ground is pushing on us. The ground is pushing us upwards. So in this case, the force applied on us, right, is positive. The ground pushed us up and we really went up. Yeah, well, good question. Okay, any more questions? Okay, so we always look at what is the system that we are analyzing, and then the force, right, comes from where. Okay. Uh, in that case, in the weightlifter case, weightlifter, we are we this his arm, right, applying force is actually the external force. The system, right, is actually the weight. So he applies this force to the weight. But when you do push up, right, at the instant, actually it's the floor. You are using the floor to apply weight on yourself. Actually, it's the floor apply the force onto us, trying to push us upwards. Okay, so let's move on. Put down by varying force. So to do varying force, right, we always will do this. We chop it up to many strips here. As if this delta x is very small. Of course, this one a bit exaggerated, because just to illustrate, right? So imagine you chop it up into many, many small pieces. Then you sum them up together. You take the force times displacement of every strip. Then you sum them up together. That will give you the total loop time. Right? You sum them all up together. But of course, we won't go and do that. Who can do that like 1 million times? Right? Maybe you chop it up into 1 million. In maths, we will come to this, right? Integration of f x. You see down here on the right, it's still a force times displacement. Okay, but when there's a dx, you can do an integration. And if you integrate, depends on where you integrate from, that will be a lower and an upper limit. So if you integrate from x1 to x2, right, you are just finding the work done from this position, is x1, to the final position, which is x2. Okay, so it's an integration. When we perform integration, also we are actually finding the area under the curve. Now we come to work done on a spring. Force required to stretch a spring. This is our Hooke's law. F equals to kx, right, for spring. Means you have a spring like this. If a spring at the equilibrium position is like this, in order to stretch the spring by x amount, you need to apply this F. Okay, so this is what this equation is talking about. F equals to Kx. And then K is just a spring constant. So it depends on the design of the spring. If K is very high, right, means the spring very hard to pull or push on. Okay? So K is just a constant for difference. So down here, we also can find the work done in stretching the spring from 0 to x by using the formula that we have just learned in the previous slide. Work done equals to integration of f dx, correct? And then now we want to know from 0 to x. So down here, this f here, substitute this kx inside. For springs out, we want to find the work done by this done for this spring. So we put kx inside here. So you will come to this expression. There is an x inside, and then you integrate dx, right? So you'll be able to solve it. Okay, you get this expression here. Actually, this half kx squared, right? This is our elastic potential energy associated with the spring. But for potential energies, right, we will touch more on next topic now, which is topic 8. Okay, but this is actually our elastic PE. Elastic potential energy. Okay. This one also lah. So work done in stretching spring from x1 to x2. You just put x1 and x2 here, the lower and upper limits. To solve it, right, you're going to get half kx squared, but x2 minus x1. So this is the elastic potential energy at position x2, and this is the elastic energy on position x1. So the difference in energy, right, must be the work done you supply to this system. Okay. So this, I say again, so this red box, you see this half kx2 square. This is the something like the final elastic potential energy. This is your initial elastic potential energy. Okay, at the final state, you have a value, right? At the initial state, you have a value. If you go and stretch the spring, the energy at the final value, usually if you stretch it, it should be a higher value. Then you minus the initial one, right? The difference in energy must be the work done you do to the system, correct? This is like the work amount of energy you supply to the system must be equals to the. Okay, so this itself, the last box here is actually a conservation of energy. Okay, and then move to the next slide. F equals to kx. This is the same thing. But this slide is to just to show you, if we say work done on the spring, which is by external force, work done on the spring, if it's half kx2 square minus half kx square 1, previous one we have seen, then the work done by the spring will be the opposite of that. Okay, work done on the spring, that means that some external force could be your hand. You go and pull the spring, right? The external force go and do work on the spring. Okay, that's a value. Then the work done, the same scenario, the work done by the spring, right, must be the negative of that value because they are totally opposite. One is work done on the system, one is work done by the system. So they will be opposite value. You can see this one is x2 minus x1, x1 minus x2. Then work along a curved path. This is actually the same concept, but let's say we are not moving along a straight line. Okay, it's from here P1 to P2 and it's curved, the curved position. Okay, actually the concept is still force times your the force that's in the parallel direction to the motion that will be useful. Okay, so you see this two line here, right? This F2 line. This means the parallel component. That means the one parallel to the motion. This is perpendicular. This is parallel. So throughout the journey from P1 to P2, right, if you want to calculate work done, you will only take into account this parallel component. This perpendicular component is totally not counted, totally wasted. Right? You won't go into calculating the work done of the system. Okay, so work done equals to F cosine phi, because we only want to take into account the parallel component. Then we go into this thing called the work energy theorem. The work energy theorem is actually derivation for our kinetic energy. So we'll see what is a kinetic energy, okay? So imagine you want to move a box from left to right. Okay? Initial velocity Vi, after that you apply force, right? So you'll start to accelerate, right? Then final velocity will be a different value. Okay, the final velocity different value. So if we want to calculate the work done to this system, work done to this system, which is the box, it is our force, this force, times our displacement, the distance for the displacement. This is when F is constant. That's why we can take F times displacement. If not, we need to do integration, right? So for F constant, we take this times this. Then this F equals to MA, we can change it to MA. So it will be MA times T. But from kinematics, right, we also know that A can be changed. This is from our V equals to U plus AT, right? From V equals to U plus AT. Then you put these values, throw inside, substitute the A. For the D, right, which is the distance, also from kinematics, we know it can be changed. To write it in terms of initial velocity, final velocity, and time. It's down here also. So we want to solve that equation. So if you change it and you rewrite it, right, work done will be equals to this, to substitute value inside already. Then you will come to this. Okay? Work done equals to half mv square using the final value minus half mv square using the initial value. So this half mv square that we see here, right, these terms, right, they are the kinetic energy. This is the kinetic energy. So kinetic energy, as the name suggests, right, is energy associated with the motion. So whenever things are moving, right, when there's a velocity to it, there is some kinetic energy. When it is totally at rest, it's not moving, right, it's stopped, there is no kinetic energy. Okay? So kinetic energy is energy associated with motion. In this case, you can see half mv square means the energy when the object is here minus the energy when the object is here initially. The difference in energy, right, must be the work you go and put to the system. Correct? This is also conservation of energy, because energy cannot be created or destroyed. The work that you put in, right, must go into converting the energy. Okay, so this is work energy theorem when F is constant. This is the work energy theorem for general form. This is when F is not constant. Remember, F can be changing anytime. So if F is not constant, right, we will need to do integration, F dx. But I won't go through the derivation. Okay, long story short, if you do that for bearing force, you do integration and you try to look it up all the way, right? In the end, you will still find the same expression. Work done equals to final kinetic energy minus initial kinetic energy. Okay, so now we come to kinetic energy, which is the half mv squared. It's associated with the motion of the body. Kinetic energy is scalar. When it is scalar, that means it is not a vector. In other words, there is no direction to it. Okay? Energies have no direction. Okay? Energies have no direction. Energy don't point to anywhere. Forces can point to somewhere. Acceleration can point to somewhere. But energy, right, we just talk about how much energy a system has. There is no direction to it. Okay? If positive value of energy means energy gain. If negative means energy loss, something like that. It is a scalar. And all energy, everything associated with energy, right? They will have the unit is joules. Work done by a force F in displacing a particle is equal to the change in kinetic energy of the particle. So this is the same statement that I've been saying. This is the conservation of energy. The work done that you supply must be the difference in kinetic energy. Okay, so if you supply work to the mesh, right, you do work, put energy to it. Of course, the final kinetic energy has to be higher than it. Okay? And if that happens, right, means the speed increases. If you take away energy from it, delta k is more than zero, means the speed will decrease. So friction is something that can take away energy from the system. Imagine a box is moving on the surface. Nothing is pushing it, but then on the surface, the box, after some time, it will stop, right? Friction is always pulling it down. So this friction, right, is taking away the kinetic energy. Converting to other forms, usually convert to heat. Okay, so let's do an example here. In a pile driver, a steel hammerhead with mass 200 kg is lifted 3 meters above the top of a vertical I-beam, being driven into the ground. You all know what is pile driver? You all know piling. Maybe some of you are even from the industry. Piling, you see the construction site, right? At the start, they will have a lot of beams. Then they want to put the beams into the ground. So they will have this kind of hammer and then keep knocking down. So at the start of the construction, you'll keep hearing dong, 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 for many, many days. That one, because they are doing piling, okay, to make the ground stronger. Okay, they drive a lot of these beams into the ground to make it stronger before they can construct anything. Okay, so this part is just talking about the piling part. One instance of the piling. From the top, try it one time. Okay, this whole question is about that. The hammerhead is then dropped, driving the I-beam 7.4 cm further into the ground. The vertical rails that guide the hammerhead exert a constant 60 Newton friction force on the hammerhead. Use work energy theorem to find the speed of the hammerhead just as it hits the I-beam, the average force the hammerhead exerts on the I-beam. So, part 1, the speed of the hammerhead just as it hits the I-beam. So we imagine this hammerhead, you see, drop down. Then just before it hits, right, there will be a speed, there will be a maximum speed just before it hits. They ask you to find the speed. Of course, the next moment it hit, then straight away very fast becomes 0. But before that happens, what is the speed at position 2? So throughout this journey also there is a rail guiding it, a rail touching it. So it's always touching the rail. So there will be a friction trying to stop this thing also. Okay, this rail is trying to guide it such that it nicely hit I-beam. So how to find that? Part A, you want to analyze the speed here, right? So you are going to draw a free body diagram. So the hammerhead, imagine, is here. Draw the forces. One is mg pointing down. It is mg. The other one, because it's moving along the rail, right? Always there will be this friction force acting in the opposite direction, upwards. Question tell you that it's 60, constant 60. Okay, now that's all. There's only 2 forces. No more other forces, right? So we can write out the equation. We use this formula here. Work done equals to change in kinetic energy. Down here, work done, right, is actually force times displacement. Force is mg minus f. This is net force, net force. Downward, net force downward. The mg minus f. So this force and the displacement, which is also in the same direction, they make up the work done. Okay, this is what we learned. Then on the right hand side, you can ask yourself what is K2 and what is K1. K1, which is the kinetic energy at the start, is released from rest, correct? Confirm 0. because when things are not moving, velocity equals to zero, right? That energy confirm no kinetic energy. Okay, then at K2 is moving at a certain speed, which we are tasked to find. So K2 equals to half mv squared. Okay, then in this whole thing, right, you have to find this V2, which is the only unknown here. Okay, all the other values we have, these F are also given in the question. The target is 60 joule. So the only unknown is V2. We can use this to find what is the velocity just before it hits the high beam. Okay, we use the work energy theorem to help us. Some of you who are more familiar with energy concept, right? Maybe you will learn before. You will also note that this part, is work done, right? Now we know it as work done. You would see that this is actually your potential energy also, which we will touch on next week, topic 8, right? Your potential energy for those who know. Okay? Just something interesting. But for now, just know it as force times displacement, work done. Okay, then the next part, the average force the hammerhead exerts on the beam. So we're going to find this force thing again, right? Draw out the free body diagram. So free body diagram looks about the same. We have mg pointing down, and because it's still moving, right? From 2 to 3, you hit already, but now you want to drive it to position 3, which is very close, 7.4 cm. But you still move, you still move means there is friction, so you're destroying the F. Okay, and this one, there's a new force appearing. Why? Because this hammerhead is in contact with the I-beam area. There will be a normal contact force pointing upwards. Okay, we are drawing the free body diagram of the hammerhead. So the normal contact force is the I-beam exert on the hammerhead. Okay, this force is the I-beam exerted on the hammerhead. That's why from here, it's trying to push the hammerhead upwards. Okay, so from here, you will same thing, almost same step. But now the net downward force will be mg minus F. There's also another n, right? Pointing outward. So there's a minus n net downward force. So we also use Hooke energy theorem. Work done equals to change in kinetic energy. Now we are looking at 2 and 3, position 2 and 3. I'm driving the thing in. Okay, so work done, same thing. Net downward force times displacement equals to K3 minus K2. For this case, K3, when you reach K3, right, the whole thing is not moving, all right? That's why K3 has no kinetic energy, 0. And K2 is half mv2 squared, okay, because it's moving. But down here, right, you know this V2 in part A you have already solved already. This half mv2 squared is not unknown. Okay, in part A you have already solved it. So this V2 is a known value. In this whole thing here, the only unknown n, normal contact force. Okay, which you will go and solve. Just a simple equation. Go and solve for n. You'll find that the value of the n is 7.9 times 10 to the power 4 n. So this is the average force the hammerhead exerts on. Okay, actually, right, whatever you calculated here, right, is the I-beam exerts on the hammerhead. Right, we draw the free body diagram. We are drawing the free body diagram for the hammer. So this n, right, must be an external force that is applying force on the body that we are drawing, right? So it's the force I-beam exert onto the. But because of Newton's third law, the hammerhead exert onto the I-beam will be the same amount of force. That's why this force will drive it in. Okay, any questions for this example? If no questions, then we continue. I think ending soon already, right? Okay. Okay, so there's this another concept called the power, very related to energy. Okay? It is the rate of doing work. Work is energy, right? Energy units. So when we say rate of, means we take this divided by change in time. In other words, power is actually energy divided by time. Okay? Then when we say average, means we take change in work, which is the change in energy, divide by change in time. That's how we get the average. The other one is instantaneous. When we say instantaneous, right? It is actually at a particular time. What is the power? Average usually we take over a certain period, right? Same as average velocity, average instantaneous velocity. Concept about the same. The average is always over a certain period. Instantaneous, we want to note at that particular moment. So this formula, right? We would want the delta t to be as small as possible. Very, very small window, such that we are finding that instant. Okay, and that will be dw over dt. So dw over dt, you can also rewrite it because work done equals to force times displacement, right? So if you pull it out like this ds over dt, remember what it is? This is your velocity, right? You differentiate s, you get v. So instantaneous power is also equals to force times velocity. Of course, the velocity is the velocity at the instant. That's why you get instantaneous power also times the force. And the units for power is watt. Is in watt. So sometimes you will hear kilowatt quite a lot, right? So that's the unit in watt. Also, there's this thing called the horsepower. Just another way of saying power. Okay, 1 horsepower equals to 746. Some industries, they conventionally they do like this, right? Until today, they still follow the same conventions. For example, when you go and look at cars, when you want to look at cars, right, you see the engine, they will give in horsepower and brake horsepower. Okay, and then the lingo, right, they will talk in horsepower. Okay, but it's actually talking about power. We can always convert into watts. These days, the brochures probably they give both. Okay. Then if you see this kilowatt hour, have you heard of this term, kilowatt hour? 1 kilowatt hour equals to this amount of megajoules. So you see this kilowatt hour. Kilowatt is a unit for power, correct? As we learned, it's a unit for power. Hour is a unit for time. If you take power times time, the dimensions, what will you get? Remember, power equals to energy over time, right? But now, if you take the dimensions of power and then you times time, you are going to get energy. So kilowatt hour is a unit for energy, not power. It's a unit for energy. Okay? Some people get confused right here because they see there's a watt. Okay, again, why is it like that? It's just convention. If you are paying your own electricity bills, right? Or if you go outside and take a look at your meter, you will see this unit. Okay? They like to use kilowatt hour. Why they don't use joules? I don't know. Okay, but this is the okay, this is how much energy you use month. It cannot be power, right? Power is how much energy per unit time. Okay? They will tell you in the previous month you use this amount of kilowatt hour, that means you use this amount of energy. Okay? And also there's this concept efficiency. It describes the amount of useful output power relative to the input power. So efficiency, right, is whatever that is useful at the numerator over the total power input. So this is the efficiency. If you see this, right, because it's power output over power input, if it's in useful energy output over total energy input, also it will be correct, okay? Because it's already divided. So efficiency may not be power. If it's energy output over energy input, also and also describe efficiency. So what's efficiency like? For example, again, like engine. Engine, there's an efficiency to it. Let's say car engine. The useful output, the useful power or energy output, right? Usually we refer to the energy that is being drive the car, which is the mechanical energy. But you burn the fuel, right? The fuel actually got a lot of energy, right? But all this energy, right? A lot go to heat, wasted, go to heat. Okay, then some go into the drive the player, battery, electrical energy. Okay, but if we are talking about driving the car, right, you will take the mechanical energy divided by the total amount of energy the fuel has. And usually these days, internal combustion engine, right, for diesel is higher than gasoline. The diesel, if it's very good, can reach 40+%, and it's already considered very good already. So you can imagine how much energy is wasted. Gasoline engines efficiency 30+%, very good already. Okay, the others all wasted. Okay, so that's efficiency. Okay, let's take a look at this example then. Done. Okay. The human heart is a powerful and extremely reliable pump. Each day it takes in and discharges about 7,500 liters of blood. Assume that the work done by the heart is equal to the work required to lift this amount of blood. The height equal to that of the average American female. They tell the height. The density of blood is given by this. Heart A, how much work does the heart do in a day? How much work does the heart do? So work, right, is energy. Energy is force times your distance, right? So you must think of force times distance. But is the uh, force done by gravity, alright, in this case? So before that, you need to go and calculate your mass. Okay, they give you in liter. This is not mass. They give you in density for you calculate the mass. Okay, because after that you want to use mg, which is the rotational force, right? Mg times the distance at the work. But before that, you need to calculate the mass. This 0.001 here, don't need to get confused. It's just a way to convert liters to meter cube. You just do it your own way. You may not need to follow this kind of thing. No, not everyone memorizes it like that. You just remember 1 milliliter equals to 1 cm cube. That's the easiest way to remember for me. 1 ml equals to 1 cm cube. Okay, just remember like that. So you can convert your own way. And volume times density, make sure the units they are all correct. That will give you the mass. Okay, after that, you will do your force times distance, give you your energy. Part B, what is the power output in watts? You have your energy already, correct? Find the power, just have to divide by time. They tell you, they want you to find for a day. Okay, so the day in seconds is just 24 hours times 3,600. Basically, this is the amount of seconds in the day. Okay, so you get a power output. Any questions? And of course, after this, we have your some questions to refer to. Okay, no questions then. That will be all for today's class. So anyway, before I end, right, I want to just now I mark attendance already. So there are some that I don't see in the chat just now. So I'm going to read out a few names. If you are here, just let me know so I can mark you as present. Okay? Oh no. There is no QR code. There's no QR code. Because now, right, I mark straight away using your attendance. I mark straight away using whoever is present in the chat. Easier this way, so you all don't need to fill in anything. Yeah. So I'm gonna read out a few names. If you are here, just let me know. Ravi Kumar, Tan Wee Kiet, Daryl, Nathan, and yeah, okay, just these three names only because these are not my express. So if you happen to be here and I miss you out, right, just let me know. Okay. Okay. So yeah, thanks everyone for attending. Good, we end earlier today. Okay. Set and okay. The rest, right? I never call your name, right? The rest I never call your name means mark already. Okay, the attendance. So only Ravi Kumar and Tan Wee Kiet is absent. The rest are all present. Okay. Yeah, thanks everyone. Okay, have a good rest. Have a good rest. Luckily we end early. Okay, yeah. You're welcome. So see you all.